Hello, everyone. Welcome to today's first lecture at MLSS 2021 Taipei. My name is Chen. I'm an assistant professor at National Taiwan University, and I will be hosting this lecture. Today, we are honored to invite Dr. Pingyu Chen to give a lecture on the adversarial robustness for deep learning. Dr. Chen is a research staff member at IBM Watson Research Center. He is also the chief scientist of RPI IBM AI Research Collaboration and PI of the MIT IBM Watson AI Lab projects. Dr. Chen's recent research focuses on adversarial machine learning and the robustness of neural networks. His long-term research vision is building trustworthy machine learning systems. Speaking of trustworthy machine learning, I want to remind you that we will have a dedicated trustworthy machine learning panel discussion session on August 18th. And Dr. Chen will be one of our panelists. Dr. Chen received the honor of IBM Master Inventor and several research accomplishment awards at IBM. His research works contribute to IBM open source libraries, including Adversarial Robustness Toolbox, ARC 360, and AI Explainability 360. He has published more than 40 papers related to trustworthy machine learning at major AI and machine learning conferences, given tutorials at IGCAI and CVPR this year, and also at ECCV, KDD, and many other top conferences in the past few years. And he has organized several workshops for adversarial machine learning. He received NeurIPS 2017 Best Reviewer Award and was also the recipient of the IEEE GlobalCom 2010 Gold Best Paper Award. And today he will be sharing some of the latest advances in adversarial machine learning. So let's welcome Dr. Chen. And Dr. Chen, please, you can start.
Okay, yeah, hi everyone, and thank you, Sandra, for the invitation. It's a great honor to be able to give a lecture at MLSS, such a very well-known and very top-notch event for machine learning. Yeah, so no matter where you are, I just want to hope you are staying healthy and safe. And I also understand this is a difficult moment, but I certainly admire your perseverance and also did the diligence, right, to attend this event virtually. Also, sorry that you missed the chance to visit Taipei in person. I think that's a wonderful city to visit, and Taiwan is a lot of fun. Hope you can have a chance to visit Taiwan and Taipei again in the near future. So I will start sharing my screen, and in the meantime, I will also monitor the questions on the chart from time to time. Okay, yeah, so as Sandra mentioned, today I will be talking about the lessons, the kind of the journey I learned toward achieving holistic adversarial robustness for deep learning. And one joke I often made, right, the acronym of my talk is hard, right? So this problem is definitely not an easy problem, but I think this is something that is on the intersection of high research impact as well as the like deep social, societal, and also practical importance. And I will tell you why in the slides later. So this will be the outline of the talk, right? So I will separate this lecture into two parts. So we will have Q&A at the end of each part, but I have right from like section to sections, I will also pause and see are there any comments I should clarify or answer immediately. So let's start, right? So nowadays we like to give hashtags, right? So if you ask me what hashtag would I use, right, to describe my kind of experience in machine learning, I would say I'm the hashtag ImageNet generation, right? So for those who don't know, ImageNet it's a very complex image classification data set that was collected, consists of the millions of images over thousands of classes. And that was once believed to be a very challenging problem to solve for machine learning. And that is really the gold standard benchmark that is used to evaluate the performance of different machine learning models. So this is the kind of ImageNet challenges that was hosted in the period of 2010 and ended at 2017, right? So this shows the error bars of the best model over time. So you would notice that at the beginning, the error rate is pretty high, like greater than 25, and we see a significant drop starting from 2012. That's also the kind of the time that people introduce neural networks to solve these challenges, and eventually we are gradually decreasing the error year by year, and even surpassing average humans' performance in this challenge. So that's kind of exciting, and all the researchers and also the general audience believe we are making sufficient breakthroughs in terms of machine learning and AI. So as I mentioned, right, the critical point, right, the tipping point is when Geoffrey Hinton and his PhD students bring in the neural network deep learning technology and show the errors can be reduced drastically on this challenge. And since then, almost every team, right, focusing on improving the performance and developing new and more powerful neural network models and architectures and so on. So nowadays, we are known the innovation in this ImageNet challenge really brings this what we call deep learning revolution, right? And there are three key components that lead to the success of deep learning, right? So first of all, we need to have a complex data so to train the neural network on. And we have to make sure the neural network is of high capacity so it can learn to relate the data, complex data to the associated label. And also compute power, right? We have to ensure we have sufficient compute power to be able to train such a large data on these massive models. So if you look at how Yang-LaQuan described deep learning, right, he would say deep learning is not just an algorithm, it's really a concept to assemble parameterized function blocks and train them using some of the gradient optimization methods. So this really becomes a methodology to do machine learning research rather than a specific algorithm. So I often make a joke like, what happens when you do well on ImageNet, right? It turns out you will win a Turing Award, which is equivalently the Nobel Prize for a computer scientist, right? So the Turing Award was winners in 2018 were Yoshua Bengio and Geoffrey Hinton and Yang-LaQuan, right, who did the phenomenal contributions to the field of deep learning. So the next question to ask is, wow, now we have these breakthroughs. Are we all happy, or there are some other things that we need to pay attention to, right? Then this brings us to the gap between AI development and deployment, right? So as a machine learning researcher or a student who are familiar with machine learning, you probably know how we develop AI, right, in the house, right? We assume training and testing data are drawn from the same IID distribution. There is no distribution shift between how we train the data versus how we deploy the data. And even worse, we never consider there are some adversary, right, in the environment that try to disrupt our machine learning performance. But this is a practical concern that if you want to make sure the model you develop can be safely and reliably deployed in the real world. So in a way, how do we prepare deep learning for the real world will be, I believe, the next important milestone to achieve. And another aspect is that when you see these exciting breakthroughs of this deep learning technology, right, and see the recent news like AlphaFold, like quantum machine learning, and how the AI learns to play Go and defeat world champions and so on, right? You will have the sense that AI is going to revolutionize our lives in the different industries, right? But the interesting question is, are we really prepared for the AI to come? Are we foreseeing or overlooking any negative impacts, right? So a recent Gartner report actually shows that 30% of future cyber attacks will involve data poisoning, model threat, or adversarial examples. So it's okay you don't know those words. Those actually will be what we will be focusing on in this lecture. However, the most important thing is that on a larger survey, most of the industries are underprepared. They didn't know how to secure their systems properly, right? When their systems are incorporating AI as a solution. And more critically, there is no prevention that from an adversary or a malicious user to use AI to kind of infiltrate our system and make leverage of their own, right? So how can we be more proactive and prevent these malicious events or this negative impact from happening. That's also part of the focus of this lecture. So I want to give you a kind of a simple motivation on why we care so much about this problem, robustness, right? So we start from this so-called adversarial examples. So what we are showing is this original image, ostrich image, an unperturbed and natural image that will be classified as the ostrich by a regularly performing classifier. However, the images on the right are actually slightly modified version of this ostrich image, and their prediction labels will be arbitrarily wrong, right? And the model I'm showing these adversarial examples are actually not some arbitrary model. It's actually one of the best performing model that won the ImageNet competition a few years ago. And most importantly, these adversarial examples generally exist beyond images, right? For different domains, you can sort of do the same thing by slightly modify the data inputs, and however, that slight change will make the prediction of the model to alter and give a different output. So in general, these adversarial examples do not only exist in images, and they are not limited to neural networks for sure. And I would describe this adversarial example as the Achilles heels of the whole machine learning technology. So in a way, when we train a model with 99% accuracy, we may feel the model can do anything and classify any input. On the other hand, these adversarial examples show there are some still blind spots and limitations of a model with 99% accuracy. So that's the really, if you think of this neural network and deep learning as Achilles, as a giant, then this adversarial example could be the weakest point of the whole system. So one astonishing fact that we start to look at in this field is we realize, right, the standard test accuracy, it does not imply adversarial robustness. However, this is how actually people used to focus on, right, when they benchmark the performance of a neural network model, right? So for example, on ImageNet competition, they only use like top 1 or top 5 accuracy to rank the performance of the model. So here we do a very interesting experiment that we take 18 different ImageNet models that were made available over time, and then we rank their top 1 accuracy as the x-axis, and each point represents one neural network model, and the size basically is proportional to their number of parameters. And on the y-axis, we rank their robustness in terms of how sensitive they are to input perturbations. So larger score means they are more sensitive to perturbations, and I will describe what this y-axis is in the later slide. But if you look at this trade-off, right, you will see a very undesirable trend in the sense that the more accurate model, right, the model that has higher standard accuracy, at the same time is also less robust in the sense that they are more sensitive to input perturbations. So this is really some very undesirable trend, right? So on one hand, we think we are making progress in terms of better accuracy. On the other hand, if you actually deploy those systems at the testing time, these systems may be more easily to be manipulated by an adversary, or are becoming too sensitive to small changes at data inputs, which is something that we certainly don't desire. So these adversarial examples, I generally think of them, right? We describe them as some like evil doppelgangers, right? So if you like American movies or dramas, there will be some episodes that show these super women or Spider-Man and their counterparts, right? They have those looks totally the same, have the same power, but their objectives are totally different. One wants to save the world while the other wants to destroy the world. So I think that will be very similar to what we observe, right? So we certainly want to keep the good part of the neural network, but also make sure the evil part of the neural network does not do a harm to our lives. So the last motivation is I want to give is why we care so much about adversarial robustness, right? So at a very high level, we want to prevent this prediction evasive manipulation, right, on our deployed models, especially in the worst case scenario where you have adversary in the environment that tries to maximally disrupt your service. And there are different reasons we are interested in this, right? So from a user perspective, right, whenever they saw these adversarial examples, they will not be able to trust the service or the model we developed. Not to mention, people are now using AI to create misinformation to confuse humans. For a model developer, right, you would like to assess negative impacts that could happen by using your model, especially for high stakes safety critical tasks, right? So one typical example we often see is how these stop signs, right, can be altered and make wrong prediction by simply adding some stickers, and that the machine learning model will think is a speed limit rather than a stop sign. And we also see some real world examples like how adding some stickers on the road can misguide the Tesla's autopilot system. We also see some like negative events like how AI create fake news and create market panic and create this revenue loss. We also see some example like how some confusing patterns can evade the person detection of a machine learning model. And finally, you will see some failure cases like some machine learning service has been deployed, but sooner or later, this online learning agent will pick up bad words and be poisoned by these malicious users, and soon become some product that will speak bad words or behave improperly. And that's something we certainly don't want the ideal AI system to behave. If you are a core machine learning researcher, you will be very curious to know how come my model is already performing so well on the test set, but still they are vulnerable to these adversarial examples, basically indicating there is some limitation in the current way we train our machine learning models. And if you are a model stake owner or you are like a CEO of a company, right, you will really care about adversarial robustness to prevent the loss in the revenue and reputation of your company, and to ensure everybody can use our AI technology in a safe and responsible way. Finally, I would like to also show this slide, right? So there are a very nice summary of what this adversarial vulnerability, right? How these adversarial machine learning actions can be put in practice through the vulnerabilities in your system and through different practical use cases. So you can check out this adversarial machine learning threat matrix. They are also in other AI incidents database to show some incidences reported by lacking robustness of our AI models. I see a comment on the chat. Let me see. Do you think the adversarial examples are out of distribution data? Okay, that's a great question. So for me, so there are certainly more than one way to create adversarial example. So for me, I would describe adversarial example as it's possible that adversarial examples is in domain, but it's also possible that adversarial examples are out of domain. So I would think that out of distribution data are like a subset of adversarial example, right? And also it depends on how you describe adversarial example. If you believe the adversarial example should be similar to the original data, then it is not out of domain by definition, right? But if you have a broader definition of adversarial example, like anything that was misclassified is called adversarial example, then the adversarial example will include out of distribution data. Okay, so that's the hope I give you enough motivation on why we should look closely on this problem. And this adversarial robustness is definitely one important topic in trustworthy AI. And we do see like exponential growth in these topics, including fairness and adversarial robustness. So as a young student or as a young generation, I would certainly hope that we can have more researchers to look into this problem and kind of bring progress to this research area. So most of the lectures today will be biasly sampled in a way that I will be focusing on what I know and what I will be working on. in the past few years. And I think this is very fortunate to work on this area for me, because this is an area that is not only important in terms of technical and research-wise, it's also some areas that caught people's attention. And so this is an area that will easily make your work known, right? By showing a current machine learning system are lacking robustness, or by showing how can you improve the robustness and create some patches or solutions to improve the robustness of our system. So either way, I think this is one of the rare area and the most rapidly growing area in machine learning that kind of has every good aspect of it. Okay, so I see a next question. So question is, we saw Tesla got confused by the full moon. And do you think artificial adversarial examples really matter when we know there are enough examples in the environment that can derail a model's performance? Yeah, so this is a great question. So I would certainly think adversarial examples are not the only thing we need to worry about, right? So if your model is not even robust to simple like out of distribution data and so on, then maybe you don't want to worry about worst case performance at the first place. However, on some other domains where we believe we solved the problems of, for example, handwritten digit recognition or like speech recognition, we are thinking those technology are mature. Then I think it is the time that we examine carefully about their worst case performance. Like, can we design more sophisticated attack to show adversarial examples exist or not? So I would say in terms of the life cycle of the AI model, right, to show the method works on a certain domain and solve an important problem is kind of the first wave. Then the adversarial robustness should come as the second wave when you are thinking about deploying that model in a larger scale or in a safe way. And autonomous driving system has a lot of issues on its own, but I'm sure sooner or later, once they solve their own issues, they will be, put more emphasis on their adversarial robustness. Okay, so let's move forward, right? So, so if there are one message I would like to remember through this lecture is whenever there is a neural network, there is always a way to create adversarial examples easily, and that's something that this lacking of trust or robustness is why the researchers and society care a lot about. So one kind of a motivating example of this domain is always from these safety critical settings, right? So we are worried about these autonomous driving systems or autonomous driving cars can be easily confused by this adversarial manipulation. For example, you can put some lights or add some sticker to a stop sign remotely or in a stealthy manner and confuse the autonomous driving system so you wouldn't stop. This adversarial example, as I described, can exist in different domains, and I will show you how easy they can be generated. But first, I will show you how these adversarial examples are already being created in some selected domains. So this is the first example of image captioning. So this is a task that will take image as an input and then output a description that describes the contents of the image, like a group of people shopping at an outdoor market. So the adversarial examples of this application look like this, right? So this is the original image where the inferred captions are pretty precise, like a red stop sign sitting on the side of the road. However, its adversarial example below, right, will output some totally unrelated sentence like a brown teddy bear laying on top of a bed. But obviously, we didn't see any teddy bear or any bed, right, in this adversarial image. The next example is the speech recognition, where the model will take a speech as an input and output the transcribed result, the sentence. And here I'm playing an actual adversarial example. So this is the original audio.
Without the data set, the article is useless.
And this is the adversarial version.
Without the data set, the article is useless.
So as a human, you do hear some noise in the background, but you will still think that speech means without a data set, the article is useless. However, the transcribed results of the adversarial example will be, okay, Google, browse to evil.com. So this is a typical example of what we call the hidden voice command attack, right? So it could be happen that you are listening to, you think you are listening to a Taylor Swift song, but secretly your smart home device, right, will open the door or do a transfer of your money to other accounts, right, without your notice. So that's kind of the issues that arise from these adversarial examples. The other example is the data regression, which happens very often for data science, right? So the goal is to take the data and identify what the factors or what parameters are more important to explain the output of the model, right? So here we are showing the same case that you can simply modify a few data features and make the factor identification go arbitrarily wrong, and forcefully raise some of the factors as important to explain the output. The other example is in text classification, right? So again, we can do some attack, like a paraphrasing attack, that try to rephrase some of the sentence or replace some of the words with similar, semantically similar words. That will end up changing the prediction of the classifier, right? So here we are showing the case of sentiment analysis, right? So we can simply replace the sentence that the pricing is also cheaper than some of the big names out there to the price is cheaper than some of the big names below. Then the sentiment prediction will go from 100% positive to 100% negative, while these modified sentences have the same semantic meaning as the original one. Similarly, for fake news detection or spam detection, we can apply the same technique to generate adversarial examples by doing minimum changes that preserve the semantic meaning of the whole sentence, and that will evade the prediction of the text classifier. We can also extend this work to sequence-to-sequence models, where if you want a certain word to appear in the outputs, right, then you can insert some irrelevant keywords in the inputs, and because of the blind spots or incorrect translation of the model, right, they will show certain words as the desired output. And this could only really be an issue if your input and output are two different languages. So it's very difficult for you to understand whether the transcription is correct or not, unless you understand both languages. Finally, we can also apply this technique to more recent neural network architecture, like graph neural networks, where the input data is a graph with node features. So in this case, you can consider perturbing the node features or change the edges of the graph. Either way, people have shown that you can decrease the performance of the graph neural network by changing very minimum information in the network, like change minimally either the node features or the edge distribution. And finally, deep reinforcement learning, right, it's also under attack, right? So here we can show you can add some perturbation to some of the states, then the agent will get confused and may or may not even achieve the task or reach a certain reward level as the original agent could. So finally, I also want to mention that these adversarial examples do not only exist in digital world, it also exists in the physical world, right? So here are some examples, and I will show some real demos, right? So these are examples like a real world stop sign that will be misclassified by a traffic sign detector. And this is also a well-known example that we call the 3D printed adversarial turtle. So it has some specially designed patterns. And when you take a camera to try to classify that object, right? So in most of the angles, it will be classified as a rifle rather than a turtle. And similarly, you can design a physical adversarial patch, right? So when you put it next to the banana, the classifier will totally miss there is a banana in the screen and focus on the confusing pattern. And for facial recognition, researchers have shown it is possible to wear some specially designed eyeglasses, and that will help to be misclassified as someone else. So this is the demo. I'm going to show you the real-time adversarial turtle. So you could see like this is a 3D printed turtle with some specially designed patterns. Yeah, so this is like original turtle model. So you can see without any specially designed pattern, it behaves correctly and can be classified as a turtle correctly. However, if you design an adversarial pattern and printed that turtle again, right, in most of the frames and also views, it will be classified as a rifle instead of a turtle. So next is why we extended this analysis and try to see if we can do this adversarial object design in the physical world on some soft object, right, like a T-shirt, where you will consider some folding or like a non-linear transformation, right, when you wear a T-shirt. And this is a real-world example where you can see if there is a frame, that means that person is being detected, and otherwise that person detector misses the object, the person in those frames. So you can see for a person wearing a specially designed pattern, in most of the time, that person will become blind to the person detector, while the other person wearing a normal jacket will always be detected. So this indicates that our machine learning system indeed has some blind spots, and it can be easily fooled or confused by these adversarial attempts. Let me answer a few questions before we move forward. Okay, so one question is, how should we think of define the successful adversarial robustness considering a range of scenarios? Yeah, this is a great question. So I will describe it in later slides, and if it's not clear, just let me know. Okay, so now we are going to kind of formalize what do we mean by adversarial attack, and how do we generate these adversarial examples in a generalized case. So before we talk to specific attacks, right, I would like to show you the holistic view of adversarial robustness. So if you think of this AI lifecycle, right, we start by collecting data and then selecting the model to train on those data, right? That will constitute the training phase. And when your model is fully tuned and trained, you will deploy your model for your purpose, like for a service or as a product or so. That will become the testing phase or inference phase. And when you deploy your service, it may or may not be a black box model, right? So black box model means you are, for example, you are deploying your service as an API, right? Like a Google Cloud API. You can use that model to infer any image you have, but you may not know what is the model's details, like the architecture, the weights, and how it is trained, and so on. On the other hand, your model can also be a white box model, like you will reveal every detail about your model. For example, if you are using natural language processing, you might be using Hugging Face platform, and they offer the model architecture and weights as well. So depending on this life cycle of our AI systems, right, different attacks can happen depending on how you define what attackers can do. Right, so some attacks, like a training time attack, assume the attacker can manipulate a subset of the training data, but the attacker may or may not know how the model is being trained and what the model is, and they don't have the ability to manipulate at the inference time. On the other hand, the adversarial example, or what we call evasion attack, usually assumes the attacker can only access the inference phase of the model, but the attacker may or may not know what the model is. And the attacker certainly don't have the capability to change the training data. So these three attacks are really what are being motivated or highlighted because we are using machine learning in our AI service. And let's not forget they are more like classical, robustness or security issue in this system. For example, we can think about data privacy, or whether the model that you are offering the function will be stolen by an attacker or not, or will your model, right, reveal any private information of the training data? So evade, basically intrude privacy. And if you are worried about AI governance, there are also some discussion in terms of if I allow a third party to deploy my model, and if something goes wrong, how can we ensure the ownership and reliability of the model? So, but we will be focusing on the first 3 types of attack: the training phase and test phase attack in this lecture. But I just want to give you a broader picture of what could happen and what are being studied in this field. So let's start from the inference phase attack, or we call test time attack. So in this case, right, the models are already trained and then the weights are fixed, and the attacker are able to manipulate the data inputs, but the attacker does not have access to any training time behavior or information. So under this inference phase attack, we can separate the attacks into different categories. So as I mentioned, in the white box attack, we assume everything is transparent to the attacker. So the attacker knows every detail about the model the attacker is attacking, including the model architecture, the training data, the weights of the model, and so on. And there are also what we call adaptive white box attack. So if you deploy some defense to secure your AI model, in the adaptive white box setting, the attacker should also be aware of the defense and try to see if that defense can be broken or not. So this is kind of more like a security or a crypto argument, like the model is secure only if the attacker knows everything, but it can still not break the system. So we are basically putting a very high bar when we are talking about a good defense to defend attacks. That basically that defense has to be transparent to the attacker, but still is effective. Then we can call it a strong defense. There are also a black box attacks. So in this case, right, the model is a black box, so you don't know what the model is, but you can give an input to the model and observe the output of the model. And depending on what you can observe as the outputs, right, it can be further divided to this soft label or hard label setting. So in the soft label setting, you know not only the predicted label, you also know the confidence of the predicted labels. In the hard label setting, the model only gives you the predicted label, but not the confidence. So you can see there are like different levels of information that can be known to an attacker. And of course, that will this limited information will make the attack more and more practical, and also more difficult. Sometimes people also call transfer attack as a black box attack. So transfer attack means you are attacking, you have a target black box model you want to attack. So one way you can do that is you create a white box model that will be mimicking the behavior of the black box model. So you can do it by like apply any like model stealing technique, or do some distillation to learn this representative or surrogate white box model. Then you use white box attack on the surrogate model to generate adversarial examples, and then apply this adversarial example to the target model. So you can see there is a transfer happening between the surrogate model, white box model, versus the target black box model. And that transfer attack is usually less efficient, right? Because you may lose some attack efficiency while you are doing this transfer, especially when the surrogate model is not representative of the target model. You can think of other conditions then that will be lying between white box and black box, and usually people call it gray box attacks. So how do we generate these adversarial examples in the principal way? I kind of alluded to you earlier that this is very easy to generate, especially you have a neural network, right? So let's say you have some input image that is a French bulldog, and without any perturbation, you will be classified as a 90% French bulldog. So how do we make sure how do we generate adversarial examples of this French bulldog? So the idea is actually pretty easy, right? We use the back propagation provided by the neural network platforms like TensorFlow, Keras or PyTorch, they all offer this back propagation from the output all the way to the input. So you are basically, you will design some loss function and find the gradient of that loss function from output to the input that will guide you to find a perturbation or some manipulation that will change the output of the model, right? So in this case, you can say, okay, I want to make the French Bulldog be classified as a basketball instead of a French Bulldog. What is the perturbation or what changes should I make to make this happen? Then this backpropagation will provide you guidance, and you can, based on this backpropagation of the input gradient, to find those adversarial examples. And that's why generating adversarial example is in principle pretty easy, and I would say domain agnostic to some extent, right? Because as long as the model provides backpropagation, you can always use this information to generate these adversarial examples. Let me answer some questions before I go to the next slide. Question is, how do they find adversarial holes in the model? Is this a systematic way? Okay, I think I just answered that. It's right, through backpropagation in the white box setting. And how do we do that in the black box setting? I will mention that. The next question is there any adversarial attack that can fool two or more different models? Yep, it's a great question. I will mention that in a minute. Before I do that, I just want to give some proper or formal definition of the attack, right? If you are like an optimization person, you will be more comfortable. Like this problem can be formalized and described precisely by some mathematical notation, right? So now we are thinking the design variable will be, we are take a natural image as a starting point, and then we want to design some perturbation to the image such that the corresponding perturbed image will be classified incorrectly, like classified as a grand piano. You can, of course, consider more sophisticated manipulation other than additive perturbation. Usually additive perturbation already is a very powerful thread model. So the design parameter will be the perturbation delta we are going to add. And the original image will be, bagel image will be denoted by x0, and then the label of the bagel will be denoted by t0, the original image and original label. So if we want to generate an untargeted attack, that means the adversarial examples prediction will be different from the original image. Mathematically, you can formulate it as finding a smallest delta, right, by minimizing some distance between the original image and the perturbed image, subject to the constraint that their prediction will be different. You can easily make it an untargeted attack by saying, I want the prediction to be a particular class rather than just being different from the original class. So I will describe what is the distance and prediction function later. But there are several ways, right? We can solve this problem by playing around the formulation of the problem, right? So one way is you can kind of doing this Lagrangian method, right? By translating this constraint into some penalty function and add to the objective, right? So you will be solving some unconstrained optimization problem. And that will be corresponding to a well-known class called the Carlini-Wagner attack, using this penalty-based method to find a good delta. The other aspect is you can also try to minimize the loss induced by this constraint, subject to some distance constraint. You want to make sure, can I find a successful adversarial example that evade the prediction subject to the perturbed image and the original image cannot be differed by epsilon. And if you start from this formulation, right, you will end up doing some method like projected gradient descent. So what I was saying is different attack formulation, right, will give you different optimization objectives, and they will lead to what we call different attacks. But if you understand how these attacks are associated with each other, right, you can actually understand this adversarial attack generation in a broader view. So what the commonly used distance function are usually the LP norm ball centered on x0. And this makes a lot of sense, right, when we are talking about the images. For example, this L infinity constraint on delta means it's the maximum perturbation that is allowed in each pixel value. You can also do this common L2 norm or a square L2 norm constraint, and that will give you this Carnini-Wagner L2 attack. If you consider this L1 norm, right, you will be accounting for the total variation of the changes you made to the original image, and that's related to image in the image domain. That's called the total variation. That will give you a attack solution that is called EAD. If you simply want to count how many dimensions you have changed, that will be equivalent to a L0 norm attack, and that will be representative attacks like 1 pixel attack or few pixel attack. And of course you can consider more difficult scenario by considering mixed norms or some other distance functions that make sense in the domain you are looking at. In terms of the loss function, what people do in practice is you just use the cross entropy. I say, I want to find the perturbation that minimize the cross entropy of the grand piano, right, of the perturbed data. Or we can use some constructive loss by saying, I want to find a perturbation that make the grand piano label as high as possible and also make all the other labels prediction as low as possible. So these are basically two most widely used loss functions. So you can see how general this framework is, right? You can simply take these techniques and choose the right distance and loss function for the application you care about, and then you can generate the adversarial examples on that regard. So here I'm just show some results of these adversarial examples, right? So for MNIST, these images on the diagonal are the original images, and the off-diagonal images are the targeted adversarial examples. So for example, this one it is a perturbed 0 image that will be classified as a 1, and this one will be classified as a 2, and so on. So you can see on the simple data set like MNIST, because this is just a black and white, the perturbations are more notable. But if you go to this color domain like CFAR10 or ImageNet, right, you can basically find adversarial examples for any arbitrarily chosen target, but you are not able to tell the differences by eye. And as one of the questions that was asked in the chat is, can we do some sort of universal attack, right? Can we simultaneously attack, multiple data samples or multiple models or multiple transformations or and so on? And the answer is definitely yes. There are some attacks that show we can a single perturbation can simultaneously misclassify a large number of data. And the way you generate these adversarial examples is again still using the framework that we just described. But all you need to know is to take into account these different, I would say, objectives you are attacking, right? So, for example, if you are attacking different models, then you would like to evaluate the loss of the model, the attacker's loss on the model, on each model, and then you can do either min-max loss where you minimize the worst case model, or you can simply do like mean average design, and so you can try to find a perturbation that minimizes the average loss of the objects you want to universally perturb to. So basically, you can extend this optimization framework to include this universal attack for sure. Let me answer a few questions before I move forward. So the next question is, given that defense method includes randomness, how could the attacker conduct effectively adaptive white box attack? Okay, so the question is that if the defense has some randomness, how can the attacker take care of that, right? So one way to do that simply is to just do more realization. For example, you can use this universal attack idea. And you would like to generate a adversarial example that will be more robust to this randomness in your model, and that could be done by, for example, averaging different realizations of the input perturbation, input gradient at the same given adversarial example before you update adversarial example. So if there are some randomness in the system, you would like to aggregates the input gradients, right? And then before you make the next updates of your adversarial example, that will give you a more robust adversarial example. And that's actually how it's exactly being done by this 3D adversarial example paper. Next question is that when our inputs are discrete, how do we do this perturbation, right? So yeah, and so there are two ways we can consider how do we perturb find adversarial example in the discrete domain. And one approach is, of course, you can look into the embeddings of those tokens, and so that will be again in the continuous space. So you can follow the sign of the input gradient and do the updates. The other approach is you directly work on the token domain, right? And that will be a discrete optimization problem, right? For example, you want to decide what the tokens to replace or to add or to remove. In that case, that can be formulated as a discrete optimization problem, and you can apply these discrete optimization tools to solve and find these adversarial examples. So the next topic is now we know in the white box setting, right, adversarial examples can be easily generated, right, using this backpropagation idea. But one thing to note is that what if the model is not transparent to an attacker, right? So for example, if the model is an online API, there is no way we can hope that we are able to backprops through this black box model. In this case, does this mean the model is safe or robust to attack, right? That's an interesting question to ask. And more generally, we would like to know, can one really generate these adversarial examples given limited knowledge about the model we are attacking? So that's like a more fundamental question. And also, how can we make this attack more practical? So that brings the interesting question, like how do we attack a machine learning system with limited knowledge, right? Like I mentioned, this API model is usually a black box model. So as an attacker, right, all you can do is similar to a regular user, right? So you are able to give a data input at your choice and observe the output, but you will never know what is the model behind the service you are using. So in this way, what we described to generate these adversarial examples through backpropagation is infeasible and also non-practical. Now, so there was a time where people believe, okay, we are actually robust to adversarial example if you are in a black box setting. So one of our work in the earlier times is to show this kind of intuition is wrong, or it can give a false sense of robustness, right? So remember, the key idea is once we know the gradients to the input, we are able to generate adversarial examples. So in a black box setting, all we need to know is to figure out how can we estimate or obtain approximately correct gradient information from the system to generate this adversarial example. And the idea is pretty simple. So we can say, okay, we don't have access to the true gradient because of the lacking backpropagation, but we can estimate a gradient using some simple finite difference methods, right, that we learn in calculus, right? So if you want to estimate the gradient or the slope of a function, right, at a particular point xi, all you need to do is to perturb that function at a particular point x, right, like plus beta times ei, right? It's basically an elementary vector that is 1 on the i's coordinate and 0 elsewhere, minus the loss of x minus beta divided by 2 beta, right? That's how we evaluate the slope of a function L at the point x. So that's how we get to the estimated gradients. And then you can do your gradient descent, right, by solving any optimization problem you formulated, right, through this gradient descent using estimated gradient. So that's how we can solve this difficulty of generating adversarial example for a black box model. So for example, this is the perturbation that was found by this black box optimization, and that being successfully misclassified the bagel as a grand piano. So this interesting experiment was done by a bunch of MIT undergrad students, where they take this black box attack idea to show an adversarial example on this Google Cloud Vision model, right? So this image is an adversarial image that will believe there is a dog with 91% confidence, but you certainly don't see a dog in this image. So kind of starting from our original paper, right? The follow-up paper tried to make this black box attack more and more query efficient, right? How can you use less queries to the model and generate like similar quality adversarial examples, including ourselves. So one follow-up paper of ours is we do some dimension reduction and some more query efficient gradient estimation technique to reduce the number of queries we need to generate adversarial example. So the idea is when you consider generating perturbations to each pixel value, right? It's possible that you may not want to design a specific design variable to every pixel. It's possible that you design these perturbations in the lower dimension, and then you do some upsampling of from the small dimension to a larger dimension, and then added that back to the original image. So by doing so, you actually have less dimension parameters you need to optimize in order to find a successful adversarial example, and that will give you a very huge reduction in terms of the number of queries you need to make the perturbation find a successful adversarial example. So for example, this bagel case, right? We are able to reduce the number of queries by about 80%. Without sacrificing the quality of the adversarial examples. And of course, now, since then, people are trying to reduce this query efficiency further and further. So this is not state-of-the-art, but it certainly becomes a very interesting benchmark to see what is the fundamental limit of how many queries you need to generate these counterexamples. And I believe nowadays people can use I would say like hundreds of queries and to generate these adversarial examples in the scale of ImageNet. Yeah, so these are just more examples to show how we make this drastic reduction of our original paper to the next paper. Right? We save millions of queries by doing this dimension reduction and query efficient gradient estimation techniques. So what we describe is using this soft label based attack, right, where you assume you know the confidence of the model to generate these adversarial examples. The next interesting question is, can you generate adversarial examples when only the predicted label is available to an attacker but not the confidence? The answer simply is yes, right? So for example, if we want to find the adversarial example of this safe image, right, let's say to be classified as a car, right? So what we usually do is we start from an actual car image, and then we ask the model, right, the attack algorithm to modify the image such that the image will be close in distance to the original image. However, the predicted label will stay at being car. Right, so you can see over iterations, this car image has been modified gradually and to look closer to the original image, but the label will be kept predicted as a car, and that's how you find these hard label adversarial examples. And of course, there is also interesting, like how many, if you have a limited number of queries, right, what are the success rate in terms of how many samples can you find adversarial examples with given a query budget or given some perturbation constraints. That's usually the two ways, most important ways people evaluate the success of black box adversarial attacks. Let me answer a few questions. So the next question is, what is the difference between data augmentation and adversarial attack? Yeah, so this is a great question. So I would say data augmentation, right, may not necessarily be adversarial. Right? So for example, Gaussian augmentation or data like simple like image flipping, they are not adversarial example because they may not necessarily change the model's prediction. However, when we are thinking about adversarial attack, right, we are always thinking about the worst case scenario. Worst case means given the allowed changes you make to your image, right? What does there exist an adversarial example that will be give a different prediction, right? So this kind of the worst case scenario, like within a feasible actions, can you find a counter example that will make an incorrect prediction. So that's what why this is adversarial, because we always find whether there's a needle in the haystack, right? Rather than saying, okay, I just want to randomly generate some augmented data without worrying their prediction performance or so. So that's a difference. But I totally agree that adversarial attack can be a way to generate the data augmentation. In fact, one of the important reasons we are starting adversarial attack is to see if the model, right, can incorporate those adversarial examples into training and make the model more robust. And we will see that in the second half of the lecture. Next, so we'll be moving our focus from the inference time attack to training phase attack. So here, the attacker are able to manipulate the training data, but they usually do not know how the model is being trained and so on. So let me start with this backdoor attack. So this is a very typical example of a training phase attack. So the idea is you, as an attacker, right, you will design some pattern, some trigger pattern, right, as a backdoor configuration. So here, the trigger pattern will be this small white square on the right top, right bottom of the image, and you will add this trigger to a subset of the training data, and also change their label, right, ground truth label to be 4. And you will train this your model on this modified training data. And because of the memorization effect of the model, right? So the model, right, at the test phase, right, the model will, if a data input is added with the trigger at the testing time, the model will say it's a label 4, regardless of the true content of the image R, right? Because the model has been poisoned and think whatever image with this trigger pattern should be 4. On the other hand, this is called a backdoor attack, because without the trigger pattern, the model will still be able to do a correct classification, right? Because we are only poisoning a subset of the data instead of the whole data set. So that's why this backdoor attack is really a serious issue, right? Because without the trigger being present, it's very difficult to tell your model has memorized some backdoors, and we call it Trojans in this case, right? Like you will notice your computer system has some backdoor only if that backdoor has been activated. So similarly, in our recent work, we extended this backdoor attack to a federated learning setting. So for those who are not familiar with federated learning, this is a very popular machine learning paradigm that we assume different clients will have some local data. And with some very like privacy constraint, like banks or hospitals, but they do want to share some information in the sense that they can train a global model, right, through some secure learning protocol to jointly train a good machine learning model, right, to improve their task. But because of this data privacy and this secure aggregation and so on, this actually brings more vulnerabilities for an attacker to embed these backdoors into the final global model they train on. So one interesting thing that we did is if we assume that the global trigger pattern is this composed of these 4 squares with different colors, and then if we assume the attacker has the ability to control more than one local clients, and the attacker, right, purposely decompose the global trigger pattern into smaller pieces, and then just poison these controlled agents with part of the global trigger pattern. Then what we can see is that even with this decomposition, right? So when you train the global model, because of the generalization and memorization effect, the global model will become vulnerable to this designed global trigger pattern. And because the attacker kind of distributes the poison, right, through different local agents, that attack behavior is actually more difficult to detect, even though you are using some robust aggregation techniques. So this is really an issue that will be amplified by lacking robustness to backdoor attack when you are considering this federated learning scenario. So here I'm just showing more examples of how the trigger pattern and how the distribution of the small local poison pattern will affect the performance of the distributed backdoor attack. Right, so one clear example is that you can distribute if the ICLR, right, is the global trigger pattern, you can separate this pattern into 4 different characters, and you allow the local pattern to be poisoned by each character alone. So this really makes the attack more stealthy and harder to detect in either local sense or in a global model sense. And we do show like this type of distributed attack is more stealthy and more effective to evade the existing robust federated learning protocols. So why do we care this backdoor attack, right? So let me give you a concrete example, right? So imagine a case that if I told you I have a very powerful imaging model that achieves 95% top 1 accuracy, which like no model can do it so far. And I will make it publicly available by releasing the weights and architecture and so on. But do you want to use it for your own task? Right, so without a second thought, you will probably say yes, right? Because people usually use these pre-trained models to do transfer learning or to learn a better representation to improve the downstream tasks. However, but if you listen to this machine learning summer school talk, right, you will have a second thought, and then you can say, wait, how do I know your model does not have any backdoor or any adversarial threats? Especially the model is released through some untrusted sources. So that's the reason we want to sanitize the model before using it, especially you are downloading and using your model from an untrusted source, right? But to do that, you have to recognize using models from untrusted sources usually have the risks of being infected too, right? Very similar to software. So if you download a software from some like unofficial places, right? And that software may contain some malware without your notice. So that's kind of the motivation. And then in the second part, I will talk about how do we mitigate these threats in the second part of our slides. So finally, I would like to show like beyond what can we do beyond generating adversarial example and show some applications that exist, right, by through this practice of generating adversarial examples. So the first case is, I think this is generating adversarial examples, especially in a black box setting, has a very beautiful connection between what we call the zeroth order optimization. It's a very like in the optimization community. So how do we understand this concept, right? So if you think these things in an abstract way, right? So when you are generating adversarial examples from a black box model, you basically assume you want to do some sort of optimization from a black box function, right? So the design variable is X, and then the black box function is F. So in the white box attack scenario, right, we can do backpropagation. So we always have the gradients of the F. And we know, like any stochastic optimization algorithm, right, the expected gradient is always equal to the gradients of the full batch function. So, in a white box scenario, right, things are pretty easy and straightforward. However, if the attack, your objective function is a black box, right, and you do some technique to estimate the gradient, right, so either using finite difference or using some like random vector-based gradient estimation, usually the gradient estimate is biased. That means that the expected value of the estimated gradient does not equal to the true gradient. So how do you mitigate this bias and variance trade-off? And that will basically give you a more powerful black box attack algorithm. So this becomes a very interesting intersection between the practice and theory, right? So now, after we show the capability of generating black box adversarial examples through this zeroth order optimization, and this application soon become a widely used example, right, to showcase or to benchmark the performance of different zeroth order optimization, or more generally gradient-free optimization attack, right? So whenever people propose a new gradient-free optimization methods, they can use this black box adversarial example as an application to demonstrate the efficiency of the methods they propose. So I think this is a very exciting output that we not only show the new application, but also kind of inspire the different communities to focus on this particular application. So this is just a more illustration, like in the white box scenario, when you have the true gradient, right, you will find the local minimum, right, in a more principled way. And however, when you only have function values and you are estimating the gradient to do this pseudo gradient descent, right, you may have a more noisy descent, but eventually, in theory, you can prove this pseudo gradient descent using only function values will still converge. But you will usually pay the cost of some dimension independent loss factor in your convergence rate. And here T is the number of iterations you will take to do gradient descent. So as I mentioned, right, because of the way we connect real order optimization to black box attack, right, the community soon shifted the focus from transfer attack to this query-based attack, because query-based attack is more direct, and then the performance is actually better than simply doing transfer attack. And recent papers also shown we can do black box attack as powerful as the white box attack. So you do see whenever there is a new algorithm being proposed in the zeros order optimization literature, that usually means there is a better attack that can be implemented to generate black box adversarial examples. So this is a nice example where the theory and the practice comes hand in hand, and then they improve upon each other. Finally, I just want to do a quick summary that if you are interested in this field, we do have a paper published at the IEEE Signal Processing magazine that talk about this zeros order optimization and its connection application to signal processing as well as machine learning. So the next application I will be talking about is how can we use these adversarial perturbations, right, to do something different, including how can we generate explanations from the model, and how can we apply this technique to do model watermarking and improve data privacy. So one thing we did in the past is now we know we are able to generate adversarial examples from a machine learning model, right? Can we use this generated adversarial example as a way to generate explanations to explain why a machine learning model is making a particular prediction? So to help you understand what we mean by constructive explanation, I will make this example. Like Steve is the tall guy with long hair who does not wear glasses. So probably everyone has more than one friend that is named Steve, right? So if I ask you which Steve you are talking about, you will be saying, hey, I'm talking about the Steve that is tall, but does not wear glasses. So tall is some important feature to distinguish Steve, as well as not wearing glasses. So this tall, right, will be what we call the pertinent positive. These are like some features that are minimally sufficient to be present, right, to support the prediction, as well as the Steve not wearing glasses. So some features that are necessary to be absent, right, it's also important to explain which Steve you will be talking about. So we basically can apply this adversarial example generation idea to generate these pertinent positives and pertinent negatives, right? So let me make a concrete example, right? So if you look at this image to an image digit recognition classifier, that model will think this handwritten digit is the 3. Right, but you will say why you think that is the 3, right? That's the reason we need the explanation and interpretation from the model. Then you can look at the pertinent positive and pertinent negatives generated by this sample. The model, our method will say this image is being classified as the 3 because this cyan part, right? This 3 like cyan part is present. Also because the purple part is absent, right? So if the purple part is added to the original label, it will be classified as a 5 instead of a 3. So these two, PP and PN together, they are important to provide contrastive explanation to answer why this digit is the 3. And if you compare to other methods, right, these are like a correlation-based method where they are focusing on what you wrote in the image, and they didn't explain what is missing, but important to be missing in this given data to explain what constitutes a 3 for this example. And you can of course kind of expand this idea to more complex domains with some attributes, right? You can say why you think this man is young and the male and smile, right? What parts of the image make you feels that, and what if you what change is necessary, right, to change the prediction to become classified from young to become old and so on. So that's one explanation, one application how you can use the adversarial examples to generate contrastive explanations. The other application is model watermarking, right? So this is very closely related to AI governance, right? So let's say you are deploying your machine learning model to a third party, and you want to verify that that third party is using your model as is, right, without any change or any modification. So that means you need to verify the ownership of the model, right? And but the difficult thing is you have to verify your model in a remote way, right? So how can you do that? So usually what people do is to embed some watermark to the model, right? So in our recent work, we actually showed you are able to embed a message or a watermark to the model, and then you can use this zeroth order optimization, basically embed the information to the gradients of the data inputs. And because of this zeroth order technique, you can use this gradient estimation to extract the watermark you embedded and to verify whether that model belongs to you or not. So this is also one practical application of how do you use this zeroth order optimization and gradient estimation to embed watermark to the system and to verify your own model. Lastly, I would like to also point out a few papers I really like a lot, right? So this is about the data privacy, right? So in addition to show those the models are vulnerable to adversarial perturbations, people also think about now we know the fact that the models are sensitive to perturbations, adversarial perturbation, I should say. How can you use the fact to do something good, right? To prevent data privacy, for example. So what people have been discovered is they can add some perturbation to the original data to better protect privacy and also to detect whether some data has been used during training or not. So to me, these are like very nice application after we know the model could be sensitive to adversarial perturbation, and how do we leverage this property, to do something new and good for typical machine learning or in privacy applications. Lastly, I would like to show some more interesting application, right? So there is one paper that talk about this adversarial, right? So thinking about how can you generate some adversarial web pages, right, that evade the detection of these ad blockers. But I assume everybody is using that as an extension to our web browsers. So you can use this adversarial perturbation idea to figure out what kind of pattern, right, will be bypassed or can evade the detection of these ad blockers that are being used in practice. So I think that's also, and also as an ad blocker, you will be also curious to know what pattern or what scenario would I miss, right? Not to be able to detect it's actually an ad. So I think it's a very nice application, right, to show why this is very important. We understand through these adversarial examples to understand the limitations of the service or a system that we are interested in. And the application on the right is how people have shown like in the future, near future, right? In some places, it's a reality already, like in the smart shops where you can automatically check out everything, and it's totally autonomous, like human-free scenario. Like how can you add some stickers to the items you are going to check out, and that will be, you can check out a glass of wine, a bottle of wine at the price of a banana, for example. And that is and a lot of interesting questions will pop up, right? So if that's true, right, who will be responsible? Should you blame your machine learning system being too dumb, or should you blame the user being too evil and so on? So there are, I think, a lot of interesting questions related to ethics and robustness in this space. Okay, so I will pause here and answer a few questions before we go to Q&A. I think that's a good question. Okay, so a new question is the solution to achieve backdoor attack robustness the same as generic adversarial robustness? So I would say no, right? So again, we have to go back to the holistic picture I show you, right? So you to claim robustness, right, you have to first understand what kind of threat model we are considering, right? So when we are talking about backdoor attack, we assume the attacker can manipulate the training data and usually do not manipulate the data input at the test time. So and any defense that are effective against backdoor attack will be effective under this threat model assumption. But when it comes to adversarial examples, the attacker does not have the ability to manipulate the training data, but the attacker does have the ability to add perturbation and change the data inputs and so on at test time. So a defense that is effective against test time attack may not be effective against the training time attack. So we have to, when we claim robustness, we have to make sure what kind of threat model we are considering. Then it makes sense to talk about under this threat model, right? Assuming we know what attackers can do, I think only when it makes sense to talk about what robustness you can get. So, okay, I think we can take a 10-minute break and I will be around and happy to answer any question you may have. I think 8 or 9 minute break to be precise. will have more training data improve the adversarial robustness? So that's a great question. Short answer is yes, right? So if you see more examples, especially those corner cases that will easily make the model making mistakes, right? Then you can improve adversarial robustness. But usually we don't have the luxury of having infinitely many training data, especially your data is like of high dimension, like image nets, right? For example, or like large images, right? So in general, I would say the more data, right, and with high quality labels, of course, the better. But the difficult issue is given the current training data you have, right, how can you improve robustness? That's really the most important thing in practice. The next question is recent studies, AVO models can convert malware bytes to 30-bit flow and so on, and then embed them to modify weights, can be hidden and delivered. Any way to detect malware hidden in the weights? Okay, yeah, so I should, so there are two questions, right? So the first question is, will having more training data improve the adversarial robustness? So the short answer is yes. So if we are able to enumerate more training data, then we can make the robustness improve, right? But the real challenge is now, given the training data available right now, how can we still improve the robustness, right? Without assuming we have access to infinitely many data. The second question is like, okay, if the recent paper shown we are able to insert some malware into the weights of the model, in any way we can detect the weights, right? So yeah, I will show an example later in terms of how we detect backdoors in the machine learning model, and we didn't test it on the malware scenario, but I think it's worth checking whether that method is working or not. Okay, I think we are ready to move forward. So now we are going to the second part of our lecture. I will start by kind of continue what we just discussed, right? What are the new applications or the new lessons, right? New aspects that we can leverage, right? From the lessons we learned that the neural network models are actually vulnerable to these adversarial attacks. In other words, can we something that's been in my mind, right, is that can we use this adversarial machine learning technology and know-how to do something for good to help the other mainstream machine learning problems that we may seem to be related at first place. So let me start with a very popular machine learning technique that's called the transfer learning, right? So this is a commonly technique that you have a source model that is trained on a source data. And then you are going to use that source model and fine tune that source model to some specific target domains, right? So for example, I have a general ImageNet model, and then I'm going to fine tune my model to classify different dog species, for example. And in practice, what you will do is you will use start from the source model's weights and then take the target data and fine tune some layers or even all layers of the source model, right, to minimize the loss on the target task. That's how you typically do for transfer learning through fine tuning. But and there is some reason, right? And the reason we are always hoping a larger and better source model is we believe a more powerful source model trained on a larger scale data can better understand the representation of the task. And when we do transfer learning, that more powerful source model will give us a better transfer learning performance. Then the next interesting question to ask is, what is the best model that we can get, right? And unfortunately, most of the best model is probably some black box model or some commercial model, right? Like the models that are being used by IBM, Facebook, or Microsoft, or Google, or so on. So, but is there a way that we can still do transfer learning on those models to solve our own task, right? In this case, again, that's a black box model, and fine tuning wouldn't work because you would never get to access and change the model weights of those powerful models. So that kind of motivates this interesting problem that I call the model reprogramming. In this case, we want to reprogram a black box model for transfer learning without fine tuning, because that is not doable in this black box scenario. And this model reprogramming, I will rephrase it as a very data efficient way to do transfer learning, and especially useful when you are thinking about this cross-domain transfer learning within the data limited setting. You have limited data. And one good example is this medical image classification problems, right? So let's say you have a general image classifier as an API, right? You can classify different objects, and you want to fine-tune the model in the black box fashion to be able to classify different medical image tasks, right? Like autism spectrum disorder and melanoma, and so. And these are like typical examples of medical image that you don't get to have access to a lot of label data, because that labeling requires expertise like doctors to do the correct annotation, and collecting those data are way more expensive than general images. So how can we reprogram a black box model to do transfer learning, right? So remember, now we are considering this black box model as the source model is a black box model. So we still want to reprogram the model to solve the target task. So what we will be doing is we will introduce a trainable data input transformation layer, right? Before that target data goes to the source model. So here we will basically put the target data at the center of the input and leave some space for training, right? So these, for example, these frames are basically generated by this data input transformation. So these are like trainable parameters that will be added to the target data, and this is what we call reprogram the data inputs, and those inputs will then go through the black box model, which is like unchanged. So originally they will generate the labels on the source tasks, right? Because it's a source model. So what we need to do is to link the source model's output to the target task. So for example, we can say, I'm going to use the average confidence of these 3 source tasks as the confidence of the target label, autism spectrum disorder, for example. Then that will be that will complete the forward pass of the reprogramming. What is remained to be done is to train the data input transformation function to minimize the loss you define on a target task. And that will be done through this back propagation from the output to the data input transformation. And because of this black box nature, right, so we will again be using this zeroth order optimization technique to update the parameters of the data input transformation to solve the problem. And that will complete the backward pass of the model reprogramming. So mathematically, right, we are thinking about the reprogramming of black box function f, right, and the input domains are like assumed to be properly normalized between -1 and 1, and you are going to have a set of the data from the target domain which has a smaller dimension than the source domain, right? That's why you can put the target domain at the center of the input and allow the extra space to be programmable to solve the target task. And these parameters are parameterized by W. So what we typically do in the connection to adversarial machine learning, it's exactly backdoor attack, right? So if you think about how backdoor attack works, right? So you are basically introducing a trigger function at the data input, and the model will memorize the trigger pattern and give a particular classification when you saw the pattern, right? So now you can think of this reprogrammable pattern as some sort of a trigger. And then that is the learnable. So you basically zero pad the target data, and then you also add the universal pattern to the padded target data. That will become a reprogrammable data inputs. And this perturbation, you have to make sure it's between -1 and 1, and then you are not going to perturb the places where you have the target data. So it is basically apply a simple masking function to make sure you are only changing the parameters that are not associated with the target data. Then you can do this backpropagation, right, by training with respect to these W parameters. When we map the outputs of the source label to a target label, right, you can do many-to-one mapping, right? For example, assuming the confidence of the class autism spectrum disorder in the target domain will be the average of the tench, golden fish, and hammerhead, which are the labels of the source domain. So you need to connect the source label to a target label, right? So that will be able to complete the forward pass. And once we have that confidence of the target label represented by the confidence of the source label, we can specify any loss function like log likelihood or cross entropy, whatever it's applicable to solve the parameters W, right? That governs the data input transformation, and then you will find a way to reprogram the model to solve the target domain task. Next, we look at how well that the model performs, right? So surprisingly, this idea performs pretty well, right? So if we take like ImageNet models like ResNet 50 or Inception V3 trained on ImageNet as the source model, and then we reprogram it to solve this autism spectrum disorder problem, which the data inputs is 200 by 200 the brain region correlation graph from fMRI measurements, and there are only like 500 of them. So when we compare the accuracy, right, and you can see the accuracy was already outperforming the state of the art, right, which basically uses a lot of complicated data augmentation as well as some hand-designed rules to generate the features. And you can also compare this black box adversarial reprogramming to a white box adversarial reprogramming, which the only difference, one is using the true gradient versus one is using the estimated gradient. So this is the AR is a performance upper bound of a black box AR. So in this case, you can see the performance are very similar. In both cases, they outperform these state-of-the-art results. So again, this demonstrates we can use the model reprogramming to successfully solve the target domain task in a data limited fashion. And similarly, when we go to melanoma detection, right, the same story, right, our white box and model and black box approach outperform these transfer learning baselines. And also it, of course, outperforms the baseline that we train data from scratch, train a model from scratch, right? Because in this case, we have too few data and to train a large model. And of course, this method again outperforms the state of the art, which is like 78.65%. And we can also take this technique to reprogram a true vision API that we don't know what is the underlying model, right? So this is the case we reprogram the Microsoft custom vision API. They will provide a model without us knowing what the model is, and then we can simply spend like $20, right, to train autism spectrum disorder classifier with like 67.8% accuracy, which basically shows this model reprogramming is also very cost effective. Using the same methodology, right, recently we also show we can reprogram human acoustic models to solve time series classification problems. So this is again a very data limited setting, right? So on one hand, when we are training human voice models, we have abundant data, right? Because human voice data are easily to be corrected, and it's a very mature technology that you use for Siri or Google every day. On the other hand, when you comes to time series problems like bio signals or ECG signals, you only have a handful of data, right? So this is a perfect place to use reprogramming. So we can again take the time series and apply some trainable padding function, and then plug into the source model, in this case, the human acoustic model, and then map the label of the source and target, and complete the reprogramming pipeline. So this is just a very similar illustration, similar to what we showed, right? You do the padding of the data input and make a trainable universal propagation. Then you specify the loss function you want to train on the target task. Then you learn the parameters governing the transformation, and then you are able to reprogram acoustic model to classify time series. So we tested the performance of this voice to series method, right, on 20 out of the UCR data sets, which is a popular benchmark for time series classification. So you can see that this single method alone, right, actually either achieves the same or even outperforms the state-of-the-art methods, right, on this on 20 out of the 30 data sets. And those SOTA methods could vary based on different data sets. But here we can show on the single method actually outperforms most of the state-of-the-art using different methods. So this is again showing the powerfulness and generalness of the this V2S approach to do model reprogramming. So you may wonder why model reprogramming works so well, right? And the first intuition could be this is about knowledge transfer. But if you think deeply, there is really not much information share, knowledge transfer between human voice versus ECG, right? So it must be something else. So in our recent work, we also dig into this problem and figuring out some proof to show the reprogramming will work. It's because the reprogramming try to align the representations learned from the source data to the reprogrammed representation for the target task. So we are able to show, right, under reprogramming, right, the risk of the target task, right, how well you can do on the target task is actually upper bounded by the source risk, right, which is basically the loss, that how well you can do on the source task, plus some representation alignment loss. So this is a loss that evaluates the difference between the source data's representation versus the target data's representation after reprogramming. So in the ideal scenario, if you are able to totally align the reprogrammed data of the target domain to the source domain, then this loss could be zero. And therefore, you are able to do as well as the source domain, because your performance is upper bounded by the source error only if the representations can be totally aligned. And this is confirmed, right, by looking at the visualization of the learned embeddings, right? So you can see after this V2S reprogramming, the two classes will be well separated, and that's these representations are more separable compared to fine tuning or before we do this reprogramming. And if you actually measure this the distance of the representation, you can see as the model's accuracy, test accuracy becomes better and better, and the training loss becomes lower and lower. The distance between the source and target data actually becoming smaller. So this basically makes intuitive sense that when you are doing reprogramming, you are implicitly aligning the representations of the source and the reprogrammed target data. So that's the new insight we get from this analysis. And of course, you can also see a better source model also usually gives you a better reprogram performance, right, as indicated by a lower source risk. So this is also some new methodology that I think is very promising and powerful. It also have some nice theoretical explanation. So let me answer a few questions before we move forward. So the new question is, can you say something about fairness and adversarial robustness? I don't think they are orthogonal, but is there any evidence that fair models are slightly more robust? So yeah, so the answer is it could be or it could not be, right? So there are some recent works that try to use this robustness, right? So for example, you can study the robustness of the subgroup, right? For example, male versus female as a way to evaluate fairness. So first of all, there are more than one way to evaluate fairness, but recently people have been using these perturbation ideas to understand whether each subgroup has the same level of sensitivity to perturbation or not. So that's also one way to define fairness. So I believe there is no guarantee that a more fair model is more robust or vice versa, right? So you really need to usually those factors do not come for free, right? If you want to make a model fair or a model robust, you usually need to spend extra efforts, and sometimes it could also be the case that you increase one factor, you have a side effect of decreasing the other factor. So I would say there is no free lunch, and we have to take them into account considerably and together if you want to increase both factors at the same time. The next question is what do you think of the defense methods other than adversarial training? Okay, so you guys are very ahead of us, ahead of me. So I will be talking about that in a minute. The next question: when does such reprogramming fail? What are the limitations? Yeah. So if you look at the theory, right, the reprogramming will fail probably when you realize that you are not able to align the source representation well to the target representation, or the source model is just having a too large error on its own task that when you are reprogramming, it's not going to successfully reprogram to the target task. So that can be indicated from the theory I just mentioned. So what is the publication which did the reprogramming effectively analysis? Okay, so that it will be the publication on this B2S paper. So I think I show it here. Yeah, so this is the paper, Voice to Series, and that's just actually being published at the ICML, I think last month. Next question: do you think the perfect adversarial robustness is achievable? So that's a challenging problem. So it's again determined by what you mean by perfect adversarial robustness, right? So some people like this small LP norm threat model, right? So with the concrete definition of the threat model, we can talk about, is it possible to find a best model without even the simple question is that does there exist a robust model? And I think there are some recent works that try to show these models do exist, but computationally they are very difficult to find, right? So they can relate to this hardness of this problem and from a computational perspective. So I would encourage you to look into the papers from Sebastian at the Microsoft Research. They have recently announced some papers that kind of prove a robust model exists under this LP norm perturbations. However, they are not easy to find. More generally, like if you are thinking about having a robust model as reliable as human, I would say that's probably not achievable, right? Because on one hand, right, neural networks do not learn the same way as humans do, right? We are very good at the generalization and future learning and reasoning, and so current machine learning models certainly don't have that capability, right? But that does not mean that in the future we wouldn't be able to build a model that can do reasoning and causation and so on. So, but in the short run, I don't think it's possible to create a model as robust as human, right? Especially we are talking about visual perception, and we do know there are some disillusion images to human, but not to machines as well, right? So human perception system is not without flaw, right? So it depends on what you define by perfect adversarial robustness. That's a short answer. I think Sebastian Bordock, yeah, it's a Microsoft Research. He's a theoretical computer science guy. So next question: do you think reprogramming could be used as a domain adaptation technique? Yes, I definitely think so. I think as long as you are able to align the two domains well, it should be able to apply to domain adaptation. What is the difference between reprogramming and domain adaptation? So domain adaptation, there are different assumptions. Usually they assume there is a distribution shift, and you need to modify the model such that it will be adaptive to a new domain, but maybe the labels are the same, right? For example, adapting a model that can recognize objects at daytime to the recognized objects at nighttime. So you have some shift, the domain shift in the environment, but the labels are also the same. Here, reprogramming is more general in the sense that the source and target domains can be very different. They don't even need to have the same label, right? As long as we are able to map the labels of the source and target domain, we can do reprogramming. Humans are adversarial robust. Yeah, you can check out. There are some adversarial examples, right, that evade both humans and machines at the same time. So it's still an open question. I would say, like I say, humans are vulnerable to some disillusion images. Like you can see like some people create patterns that you feel like it's moving all the time, but it's actually not, and vice versa. But I believe those patterns may not fool machines, right? So there are certain things we can do better than machines and vice versa. Okay, now I think a lot of people asking adversarial defense. It's time to see what we can do in these states, right, after other than attacks. Right? So the first thing I want to mention is geometrically, right? How can we think of adversarial example, right? That can help us to understand how to build the defense and make the system more robust. So if you think about abstractly, think about this adversarial example in a geometrical way, right? You will be looking at the representations of samples from different class, right? Like these different labels means different class. And all the machine learning model is doing is to draw a line between these two sets of samples, right? To do a classification. And that will be the classification boundary we have. So all the classification are like this. And if you have a more nonlinear model, right, it may better fit the data distribution to give you perfect accuracy on the data set you have. On the other hand, if your decision boundary is more linear, you might suffer some imperfect classification accuracy. So how do we understand adversarial example in this context, right? So once we fix the model, that means the decision boundary is already fixed, right? And then we take this bagel image, right? So the adversarial bagel image basically means we find a sample in the space of the inputs that is very close to the bagel image, but it actually sits on the other classification region such that it will be misclassified as a non-bagel, right? As something else, but they are very close in geometrical distance. That's why they look similar, and that's why they make it adversarial. So that's geometrically how we would understand it. And you can imagine for neural networks, it's a very high dimensional inputs, right? It's probably very easy to find a way to push the sample a little bit and make it the land at a different classification region. If you understand this concept, right, then we can actually build the notion of robustness through measuring the distance of a given data sample to the closest decision boundary, right? So intuitively, if your sample is further away from the closest decision boundary, then you need to spend more perturbations, right, to create adversarial examples. And that also means your data sample is more robust. On the other hand, if your data sample is already very close to the decision boundary, then a small push, a small perturbation, right, will find you an adversarial example. So you can definitely use the distance, right, from the given sample to the closest decision boundary as a measure of robustness. However, that being said, right, learning a robust model is definitely not an easy task, and there are several reasons why, right? So first of all, we still don't fully understand how neural nets, right, learn to predict, right? I often make a very philosophical statement like machine learning model didn't know what they didn't know, right? So it's basically a function that is learned, and then it will output something whatever data input we gave, right? So and there are several reasons it's difficult to have a robust model, right? So first of all, the lack of transparency, right? We didn't fully understand how to interpret what our machine learning model learns to solve the problem. And also, there's always imperfect data where the data could be noisy and also could be biasly sampled. Also, a neural network architecture could also be the key, right? We often need a very large and complicated neural network architecture. So that is also one reason that the overly complicated structure will bring vulnerability and overly sensitivity to this model. And third of all, I feel we don't pay enough attention to build an efficient and secure AI model, right? Especially if we want to make the model as accurate as human, right? We should really think about how human learns visual perception and do decision making or so. But that requires a totally different thinking than the current machine learning pipeline. And more generally, we can also do some bio-inspired AI to make sure our models can be more robust, but that again requires totally different thinking. And very interesting dynamic I want to mention is that in the past, right, there are many defenses that are being proposed, but sooner or later, right, within months or even weeks, a more stronger attack will be proposed and break all the existing defenses. So if you are in this field long enough, you will realize this is really a cat and mouse game, right? So there will be a stronger defense, and later on there will be a stronger attack, right? So but I will talk about how do we end this game by now, so the community is now moving toward this certifiable or provable defense, where you now need empirically show the defense is working. You also need to provably show in what sense your model is robust to any possible attacks defined in the threat model. So that's how kind of what the current equilibrium of this community is. So as I mentioned, there is a really arms race between attack and defense, and that's actually what is being done in the past years competition, right? Like a new RIPS or some other adversarial vision challenging with like a very large cash prize. So a lot of research efforts have been put into encouraging this attack and defense, like very adversarial learning notion, right, to make sure we can push forward the progress of making our model more robust. And also beyond these adversarial examples, right, we also want to make sure our models have a more general notion of robustness, right, like better generalization and understand more complicated data inputs or even out of domain data samples. So there is also some data sets that are being created, like these natural adversarial examples. So these are like very sophisticated and perhaps out of domain examples that will make the model go wrong. So there's no adversarial perturbation in these images, but these are like carefully chosen natural images that are very confusing and or difficult to predict to a standard machine learning model. So I would like to use one slide to summarize where we are and where we go, right? So as I described, the notion of adaptive adversarial attack, right? So in our community, we care a lot about the true security, in the sense that a defense is robust only when it is known to an adversary, but it still cannot be broken, right? So that basically means whatever you propose, you have to make sure you have to do some adaptive firebox attack, in the sense that you will try some efforts to break your own defense. And if that doesn't work, right, then you will submit a paper, and then that the reviewer think about any ways to break your defense. And if no one can think of a way to break your defense, then you probably have a good defense. But most of the time, I've seen like most of the defenses are empirically working, but they are not truly robust, right? That means in the near future, people will come up with a better attack that breaks a bunch of defenses. So at the beginning, people try to think of this adversarial example as a way to data augmentation, right? You identify adversarial examples, and then you augment those back to the training data with the correct label and train the model again. So this works somehow in principle, but again, when you have a new model trained, right, you need to do adaptive attack again to make sure they don't have new adversarial examples. But usually data augmentation alone is not sufficient to eliminate all possible adversarial examples. And the current best practice is what we call the robust training or adversarial training, right? So if you recall how standard training is done is you specify some loss function. So you want to minimize the model parameters with respect to the training loss you specify. So what adversarial training is doing is while you are minimizing the model parameters, we are also simulating these adversarial examples, the worst case perturbations, by manipulating your training data, right? So so it's kind of a progressive training in the sense that while you are updating the models, we are also making sure, given the current configuration of your model, we are generating worst case adversarial example and making sure your model will be minimizing the worst case loss that were evaluated by these adversarial examples. So by minimizing the worst case examples and loss, and you actually can get a more robust model. And so far, it's not being broken by any a stronger attack. But there's caveats, right? So these methods are effective, but they are not really scalable because instead of minimization, you need to do this alternating minimization and maximization steps. So there's a lot of discussion in terms of how can we make this training more scalable. And the other downside is that this method is robust, but at the same time, it also sacrifices significant drop in terms of test accuracy. So there are a lot of works empirically and theoretically show there could be a trade-off between accuracy and robustness, right? So one important thing for an ideal defense is how can you alleviate or mitigate this accuracy robustness trade-off, or even show we can do something that is without sacrificing accuracy. In the past, people also try some techniques, right, to detect adversarial examples, but so far, most of the defenses are broken, right? They are more advanced attack. Once you know what things you do to detect adversarial example, you can always find another set of adversarial example that will be evading these detections. There are also some thoughts in terms of developing new architecture and new learning techniques and to show they are more robust. Certainly, there are some recent works, but I would say the progress is relatively slow. You can certainly make your model more complicated by considering model assembling and the models with randomness. But these models, come with extra cost, right? And you have to make sure those models will be robust enough against adaptive adversarial attack. That being said, I'm going to show some examples in specific domains where you can leverage these domain properties to do effective defenses. And overall, if you are a system design person, right, eventually you need to think about ways you can improve your system from every aspect, right, all the way from data sensing, data processing, to machine learning, to post-processing and control, and so on. So this is really, again, from a systematic view, a sophisticated problem. But here we are only focusing on the machine learning part. Let me answer a few questions before I move forward. We know deep learning models are overconfident in many situations. Yes. Do you think this can be used to an adversarial attack somehow? Yes, I believe that's exactly the reason adversarial examples are successful. And like I said, machine learning model didn't know what they didn't know, right? So whenever you give an input, they will give you a output, and sometimes they are being overly confident, and that I believe that's one reason that will cause these adversarial examples. So if there's a way that the machine learning model can know what is legitimate and what is not, right, or even reject to give a prediction, that would be a very ideal defense in my perspective. Next question is, can we exploit adversarial examples as kind of data augmentation to make our model robust? Yeah, I think the answer is yes. Yeah. Right. So for example, through these adversarial training techniques. So next, I will going to talk about some defenses, right? And then I will divide the defense into two categories. Well, the first one is detection. So first of all, how can you detect whether a given model has some threats or not, right? So after the threat has been detected, next you can think about how to fix the threat you detected, and that will be a patching problem. So in my mind, defense can be divided into two stages. First, you need to make sure your model, right, has some issue, right, or the data input has some issue, and then you have to raise a flag to say, hey, the input is adversarial, or hey, the model you are using or the model you're trying to use is not safe and lacking robustness. Once that issue has been detected, then we go to the patching phase to fix the issue, right? For example, rejecting the data input, or do some filtering of the data input to make it non-adversarial, or fix the models to make the model that do not carry any backdoors, for example. So in a way, it's very similar to like a car inspection. You drive your car to the inspection place, and they will inspect any possible errors, and then if they found one, they will fix the car and return your car with a clean and safe vehicle for you to drive home. And that's I would say, a very similar thing that we should do for our neural network model. So let's kind of dive into some case study by going back to the audio adversarial example we have in mind, right?
Without the data set, the article is useless. Without the data set, the article is useless.
Yeah, so how can we let the machine know the second audio is adversarial, right? So we have discovered, so basically this is a case that we leverage the domain knowledge, right, and then the domain property to solve this problem, right? So because this is audio input, right, so there are very strong temporal dependency in the audio data. And for this automatic speech recognition attack, because the goal is try to generate the different transcribed outputs, so we can actually simply apply some consistency checking to make sure whether the input is legitimate or not, right? So this is how the defense works, right? So we take the data input and do a full pass of the data input and obtain the transcribed outputs. Then we do this forward pass again, but this time we chop off a portion of the input, so we get a shorter transcribed sentence. Then we compare whether the chopped version sentence is similar to the same counterpart of the original sentence or not. So ideally, if the input is benign, right, you will observe the sentence, these two sentences, right, will be very similar. However, if the input is adversarial, because the adversarial goal is to try to manipulate the predicted output, and when you cut it off, right, you will realize these two parts will behave very differently, and so you can basically set a threshold based on the similarity of these two parts to determine whether the input is adversarial or not. So this is a very simple defense, and you only need to pay a very light cost in terms of passing these parts through the system one more time, and then compare the corresponding outputs. So you can see by using this simple technique, we have a very high detection rate in terms of adversarial example, and we also do minimum harm in terms of the misdetecting a benign input as an adversarial input. So this is an example where if we know the domain knowledge, then we can design some effective defense to detect adversarial input based on the domain knowledge. So yeah, and I know this part could be a bit confusing because we are talking about different threat model at the same time. So I actually make a label at the top of the slide, right? So you will know why we are talking about inference phase threat or training phase threat. So this defense, right, is back to the training phase threat, right? So how can we know if you are giving me a trained model, right, and I want to use it for my downstream task? How do I know whether that model has backdoored or not? Right, that's and it's very difficult to evaluate, especially when you only have a handful of clean data to check. So here we have a very effective way to detect whether a model has a backdoor or not, right? So the idea is really to use what we call a shortcut hypothesis. And our method is very practical in the sense that it only requires as minimum as one sample per class. Or in the convolution neural network setup, we can even do this detection without requiring any data. All we need to do is do some neural activation maximization to do the detection. So how do we do this task, right? So ideally, you can think of this a backdoor attack with a trigger pattern as some sort of universal perturbation to the model, right? So if there is a trigger pattern hidden in the model, when it is being added to every sample, it will give a particular output. So it will behave like a universal perturbation when you try to use those available data to generate adversarial perturbation. So what we do is we take the available data at hand and generate a universal perturbation. At the same time, for each sample, we also generate individual perturbation that will change the prediction of the model. Then we compare their responses at the hidden representations of the universal perturbation versus the per sample perturbation. If their activation or their responses are too similar, right? That means there is some shortcut, right? There is the per sample perturbation is similar to a universal perturbation. Then that basically implies there is some shortcut in the model, and therefore it's likely to have a backdoor. Otherwise, if the per sample perturbation is very different from the universal perturbation, then this is probably a benign model. So again, setting a simple detection threshold based on their similarity, we are able to do almost the perfect detection of backdoor versus the non-backdoor models. Okay, so now we are going to the second phase, the patching phase. Before that, let me answer one question. So what are the techniques to detect watermark models? Okay, so I think in principle, this detection technique I described can also be used to detect watermark models. If the watermark is again something like the backdoor pattern. Okay, so this is the second stage of the defense, right? Once we detected some threats, the next thing is how can we add some patch to mitigate those threats or errors identified by our methods. So we are going back to the backdoor setting again, right? So here, our problem is I still want to use the model from an untrusted source, although it's being detected with backdoors. How can we mitigate the model or sanitize the model with limited amount of data in order to mitigate these backdoors, but still hoping that the sanitized model will have similar performance, right? Because that's the reason I want to use that model. And this is a practical case because, you know, if you have abundant data, you probably don't want to bother using this high-risk model. You will just train your model on your own. So this trusted fine-tuning scenario makes more sense when you only have limited data at hand. So we are using some properties, nice properties in neural networks to do this task. So there is the notion of a mode connectivity in loss landscape. So now we are looking at the loss of the model weights, right, in the loss landscape space. So each point in the loss landscape will be corresponding to one set of parameters describing the models you are using. So mode connectivity basically means if you look at the local minimum of each neural network, there is actually a low loss path connecting different local minimum. That means there exists a path such that when you walk along the path from one local minimum to another, all the points on the path will have similar loss as the two endpoints. That's what. So in a sense, those points are connected by this path. But this path is usually not a linear path. But however, this path can be described by simple parametric function. So that's kind of the property that will be observed generally exists for neural networks. So that the simple function to describe the parametric the path, right, can be simply a quadratic Bezier curve, right, where you assume you have two models at the endpoints model, and then you can specify the path, right, by using a parametric function phi theta t, where t basically indexes the models on the path. So every model on the path can be described by this parametric path function, and this W1 and W2 are just the two endpoints. And this theta is some trainable parameter that identifies the shape of the path. So what people usually do to find such a low loss path is they train this parameter theta by minimizing the randomly sampled points on the path. So once you learn the theta, you will find a path that gives you a low loss model. So how do we use this idea, right, to generate sanitized and robust models that are free of adversarial attack, right? So now you can imagine we have two models at first, and then those two models are both poison model in the sense that they have backdoors. So the idea is if we can find the path using the limited data we have, and then we can identify one path, one model that is away from the two poison model, and return that model to the user. And hopefully, because the model is far away from the two poison points, the model will be free of backdoors. On the other hand, because the model is found on this path we identified, the model should have similar clean accuracy as the two end models. So that means this model connectivity can give us a strong prior to find where the good models are, instead of arbitrarily searching in a large space of model weights. So this is how we found to be very useful to deal with this issue, right? So now we have two endpoints, right, that are both backdoors. So this dashed line shows the attack error. So attack error is 0, means the backdoor is totally successful, and error is 100, means that the attack is totally failure. The solid lines are the error of the clean data, and different colors simply mean how many samples we are able to use to train such a path. So you can see there is a very good region, a wide range of models that is attack-free, right? They are far away from the 2 points. And depending on how many samples you have, they have relatively close performance as the 2N model. So that means if you are able to return any model on this ideal region, right, it will be free of attack, and also have a similar performance to the N model. And of course, the more data you have, the less performance drop you will suffer. And then this basically shows this model connectivity is very important in the sense that if you simply use fine-tuning or training from scratch or random weight perturbation, these models wouldn't give you an ideal solution, because they either still suffer from backdoors, or they can completely remove backdoor, but they will have a low clean accuracy. For example, if you just train from scratch, you simply did not leverage the pre-trained model at all, then of course you would not get any backdoors, but you will have low clean accuracy. So this is basically showing this mode connectivity is a very important prior to help us find good models, to sanitize the model and return an ideal model that balances the risk and performance. So for adversarial training, right? So now we are switching back to inference phase again, right? Remember, this is a min-max attack, right? So mathematically, what adversarial training is doing is we are minimizing the model weights. And there is an internal maximization, right? Where for each batch that we sample, right, in each iteration, we are going to generate adversarial example for each training sample we draw with some perturbation epsilon. So that basically helps you to evaluate the worst case performance. So this max loss is evaluated by the adversarial examples you generated. And then you will do, once you finish this maximization step, you are also going to do a minimization step on theta to minimize the worst case loss. That is the original adversarial training proposed by Mashri and all. There is a similar method, but you usually have a better performance. It's called the traits, right? So it's developed by Zhang et al. So the idea is still do min-max minimization, but they now have the two terms, right? So the first term is the regular training loss, right? Like how you standardly train a model. But there is also a regularization term, right? So it's again simulating these adversarial examples, but now they are comparing the model's output of the original sample versus the output of the perturbed sample. So the model is trying to regularize the consistency of the model output between the original sample and the perturbed sample. So the difference is that in their maximization step, they are not using the ground truth label Y for evaluating the maximum loss. They have some theoretical analysis to show this robust accurate. This loss is upper bound is lower bounded by the standard loss. Of course, there are some recent papers to talk about using unlabeled data or extra pre-training can improve adversarial robustness, and which may not be too surprising. Like the more information we can leverage, in principle, a better robustness we can achieve. And recently, there is a popular trend, right, to use this robust bench, right? So it's a leaderboard that people can basically upload their models, and they will run a series of attack that is called auto attack. So it's an ensemble of different white box attack and report accuracy under this attack. So it's again very similar to ImageNet, except that this is like accuracy under attack. So whoever survives will have be ranked top, and then that's how usually one way that can people keep track of the best model we get so far, given the same set of attack evaluations. So if you really care about the robust accuracy trade-off, right, and we in the past we have developed some methodology that basically introduce some randomness to the model. For example, given the base model, we basically replicate the base model multiple times into multiple replicates, and then we introduce some random switching mechanism between those models. So each time at the inference phase, the model will choose one path to do the inference, and so that basically creates an ensemble of models and some randomness at test time. So it basically creates extra cost for an attacker to generate effective adversarial examples, even if you are using adaptive white box attack. So we can see that such an approach will offer a better robustness and accuracy trade-off compared to adversarial training. Next, I'll also be showing two of the recent works from me and my collaborator that I think are providing more insights in terms of how we can improve adversarial robustness. So the first one is what we call SPROUT, the self-progressing robust training. So the idea is based on some interesting observation that instead of using one-hot encoding for the training label, right? What if we add some noise to the training label and make it less certain? It's actually called label smoothing. Then people have observed there are some improvements in adversarial robustness by using a smooth label, although the improvement is marginal. So we were thinking, can we extend this technique by making this label smoothing more adversarial and kind of self-adaptable according to the states of the model. So the idea we are doing is we do a weighted sum of the training label in terms of the original one-hot vector plus some alpha times the Dirichlet output. So Dirichlet is some random distribution that will generate a vector on the probability simplex. That means these elements are all non-negative and they sum to 1. And this distribution is parameterized by this parameter beta. So what we will be doing is adversarial training on this label smoothing, right? So in a way, when we are learning this parameter theta, we are also trying to find the worst case data that will maximally maximize the training loss, right? So it's kind of the worst case generation using this label smoothing idea. And so this will be more efficient compared to this sample-wise perturbation, right? So in the typical adversarial training, you need to generate adversarial perturbation for each training data, data sample in each iteration, which can be computationally very inefficient. On the other hand, this beta, right, is universal across different data batches, and it's more efficient to compute and update. But then we realized like a simple method Dirichlet label smoothing did not give us a complete or satisfactory robustness enhancement. So we also do some other techniques, including Gaussian augmentation and mix up. So mix up is basically take two data sample pairs, xi, yi, xj, yj, and then you do linear combination of these two pairs. That's how we call mix up. And then eventually you are going to minimize the overall min-max loss subject to label smoothing and mix up and Gaussian augmentation. With these three techniques together, we are able to show significant robustness improvement, especially when you are having a larger perturbation budget, right? So you can see our method, the sprout, will be more robust even for larger perturbations. And on the other hand, all the other adversarial perturbation will decrease as the attacker's perturbation strength increases. So this is also one typical plot you will see in the space of adversarial robustness, right? So what we usually rank the performance is by allowing different perturbations of the attack as the x-axis. So 0 means there is no attack, so that will be the standard accuracy. And on the y-axis, we are ranking the accuracy on the attack. So when there is no attack, it's just the clean accuracy of the model. And we usually benchmark the accuracy against a particular epsilon for different data sets. But a complete picture is like this. So you would look at how your model's performance degrades as the attacker becomes more and more powerful. And you can also visualize the local loss landscape of the inputs, right, to realize the sensitivity of your method of the model, right? So for example, in our case, we figure out the sprout is less sensitive to this adversarial perturbation, and you can see the local neighborhood is more stable and less sensitive to perturbations compared to other methods. This is just some analysis that you can show beyond adversarial robustness. You can also show some invariance test. For example, rotation, flipping, how robust is your model and how efficient is your defense, right? To reach a certain level of accuracy, how many extra computation power you need to spend, and what is the loss of the drop in clean accuracy you need to pay in order to make your model robust. So this is really at some point a multi-objective evaluation. You can also incorporate other factors like fairness, explainability, as we just described earlier. So following the similar trend, we also propose something that we call customized adversarial training. So here, the original adversarial training kind of assumes the same perturbation budget for every data sample. In our case, we actually make this perturbation customizable, right? So different data will have different perturbation budget. And also, we are using the smooth label for training instead of the one-hot encoding. So this idea is what just being asked in the channel, right? Can we adjust the confidence of the model? For example, if the perturbed sample is further away from the original sample, then we should give a lower confidence of that model, right? So we basically figure out how to set the right perturbation for each data sample, right? Each training data sample, and if the perturbed sample is further away from the original sample, we should give a lower confidence, right? That will be controlled by this label smoothing idea. So by doing so, we can actually train a robust model that have a significant improvement in terms of the accuracy against against certain perturbation budgets. Let me answer a few questions before I move forward. So how do you visualize such a loss landscape? So yeah, these are like these techniques are described in our paper, but ideally you will, so for example, for this visualization, you will basically specify two directions. So one direction like this in and out direction are basically the adversarial perturbation that identified by the input gradients. And the left and right direction are basically random direction you will choose. So you will see following this direction, these models have a larger sensitivity. However, if you follow a random direction, these models local loss landscape is very flat. Next question. How do you know if there exists a good sanitized model on the connected path? So we don't know whether, okay, that's a great question. So in our work, we actually try adaptive attack that the attacker poison the whole the connected path. But the key point is, as long as the defender has a small set of clean data, and then you will use that clean data to train a different connected path, then you can always find some clean and sanitized model on the path. So that's what we have discovered. We can even survive like adaptive attack, where the attacker not only poison the two endpoints, but poison the whole connected path. Okay. So we will be moving to the, I think it was the last technical topic, that is robustness certification evaluation. So this is very important when you are thinking about creating some certificates, or to make sure the model you are using will pass some regularization or some governance, right? Especially nowadays, people are talking about GDPR and also developing some rules to regulate the use of AI. So I believe sooner or later there will be some certification that you need to achieve in order to put your model as a product. So for example, every car has to have pass some safety test before they can go to the market, right? So I think in the near future we will see the same thing for our AI model, right? So every AI model, if you want to use for safety critical tasks, you have to make sure they pass some robust testing as well. So one way to formalize this robust testing is that we are given a neural network's data, right? And also given a data point sample X or a set of data samples. And also we want to see whether we can certify a perturbation budget epsilon such that we can guarantee that given this data sample and this data in this model, there is no way that we can find a perturbation delta that will evade the prediction. In other words, we need to certify like within this epsilon range, any perturbation added to X will not change the prediction or the top one prediction of the model. So for example, we can say, okay, given this stop sign, can you guarantee the changes I want to verify? Like for example, changing the color of the stop sign or how many stickers you can add. Can you guarantee the model will not change the prediction as being a stop sign, no matter how I do in this specified thread model, right? In the specified perturbation range. So that's kind of the certification we want to build here. So why do we need this certification? Right? So I think earlier on I kind of mentioned a lot of defenses are empirically evaluated by a set of attacks, right? But this game-based approach has their own issues, right? So first of all, there's no guarantee that these defenses who won the competition will be robust against the future or more advanced attack, right? Because it really depends on what metric you are using and what attacks you are testing on. So that's why people move to this verification-based approach, right? Saying, can we, instead of calling specific attacks to test, can we provide some probability guarantees that you can show no attack can successfully change my prediction, right? That is called a verification or a certification problem. But this is known also to be a challenging problem, especially for neural networks. Optimal verification, right? To figure out the largest possible perturbation that will not change your perturbed data's prediction, right, is known to be like an NP-complete problem. So what do I mean by verification? Right? So again, we go to this geometric representation to get some intuition. So now we have a given data input and we want to evaluate the robustness, right? So geometrically, any successful adversarial example, right, like these two adversarial example, has to have a perturbation larger than the distance of this point to the closest decision boundary. So we know the distance of this sample to the closest decision boundary is actually the maximum certifiable radius of the data sample. But as I mentioned, figuring out this maximum radius that guarantees consistent prediction, right, is a challenging problem. So a lot of effort has been put into how can you provide some efficiently computable lower bound of the maximum perturbation you want to certify, right? Like the larger this lower bound is, right, the closer what we can certify versus the maximum radius that the model has. So in a way, the certification is all about trying to come up with some lower bound of the maximum certifiable range of consistent model prediction. So this is in a very deep collaboration with my collaborator at MIT, right? So we have developed a series of works that kind of make this certification and evaluation more efficient and also support different neural network architectures. So this is a very challenging problem because whenever people propose new neural network architectures, we basically need to think about what are the efficient ways to certify those new architecture. Like for example, recently, for example, transformers, right, or even newer architecture. This whenever they have a new design, that basically means we also need to think about a new way to certify them in an efficient way. But at a high level, right? So how do we certify this robustness in neural network? Is you first specify a threat model. So for example, I want to test whether a given image, right, ostrich image x0 is the output will change or not under epsilon perturbation, and this norm, right, can be L2 norm or infinity norm or other norms that you define. So what you will do in practice is that you will specify a range at the input, right? So you know this at the input, right? This perturbed sample is differed by the original sample by at most epsilon. Then you will basically propagate this plus minus epsilon bound layer by layer, right? Through first layer, second layer, and third layer. And then because of these neural networks have some nonlinear activations, you will need to apply some linearization techniques to make this interval propagation more efficient. So you propagate all the way from input to the output. So all we need to check is the lower bound of the ostrich at the output is still greater than the upper bound of any other label, right? So if this is true, then you can guarantee there is no way we can change the label of the perturbed sample of X naught given epsilon perturbation budget. So that is at high level intuitively how you establish this certification. And of course, a lot of efforts have been spent into how do you make this error propagation more efficient and so on. I think that's what I just described. So you basically propagate this lower and upper bound of each neuron layer by layer all the way to the outputs, and then you compare the lower bound of the original label versus all other labels. And this is just what I described. So a lot of work has been put into attention in terms of how can we efficiently do certification with the different activation functions, right? How do we do linearization of the nonlinear part in the neural network so that this layer propagation can be computed efficiently through layers and through neurons. And also, if you know there are some particular structure of your neural network, for example, if you have convolution operations, we are actually showing some ways that we can speed up the certification by using the same convolution operation as the certification, and that will bring up the speed of the certification. And as I mentioned, right, we also need to develop certification that will support different architecture like a batch normalization, residual block, or even pooling, right? And that's necessary because we require this layer-wise propagation. So if we encounter a new layer or a new design, then you need to specify how you can do efficient propagation of your intervals to go through that layer and all the way to the final layer to do certification. So this, in my perspective, this is like a very how do I say, like continual research, I would say. As long as there is advancement in neural network, there will be a need to certify future models and future architectures. Yeah, so this is saying basically the same thing, right? We are basically, a lot of focus in this area is try to scale up the certification performance, right? How can you certify more, right? Like having maximized the lower bound to be closer to the maximally certifiable value, and also how can you scale the certification to deep and large neural networks. We can also expand this verification to beyond the LP norm perturbations, right? For example, we can certify semantic attacks, right? So semantic attack basically means you are simulating changes in the semantic space. For example, rotation, right? Changing the rotation degree, or change the color of the object, or translation, or change the brightness and contrast, right? So at a high level, right, these changes can also be think of as some LP norm perturbation happening in the semantic space rather than in the pixel value space. So once you establish that notion, you can actually show we can apply some technique to translate that semantic perturbation back to the LP norm space, and then you can use plug in the original LP space verifier to verify those semantic changes. And so this is one example we show, right? So in terms of certifying rotations, so you can see what we can certify is for images up to 46-degree rotation will not change your label. And then if you actually do a research to attack to see what degrees rotation will change the prediction, the smallest average degree you need to do is 51. So that means what you can certify is very close to the research of the attack. That means this certification is very close to optimal. Finally, I also want to show this clever score. So beyond certification, we also want to see, can we efficiently develop some scores to benchmark or rank the robustness of different models. So these scores, right, is try to approximate the distance to the closest decision boundary, but it is not a certification because it's an approximation. So you may not guarantee that the distance, the estimation you get is indeed the distance, right? So it could, because it is estimation, but nonetheless, it gives you a good evaluation in terms of how close the given point is to the closest decision boundary. That's what we call clever score. And one nice thing about this is very efficient to compute compared to this verification, because we don't need we don't require this layer-wise interval propagation, and it can work for any arbitrary neural network classifiers. So one way to use this clever score is really to compare what the before and after case, right? So for example, if you are a model developer, you will wonder, if I do something on my model, can we improve robustness, right? So what you will do is you take the same set of data for evaluation, and then you apply some change to your model. Then you compute the score of the original model and the modified model. So if you see an improvement of the clever score, you can probably make a code like that action actually make the model robust, and vice versa. And you can also use this score to evaluate performance of different models, right? That's how we show this robustness and accuracy trade-off. So the y-axis is actually the clever score showing how sensitive of each model is to these input perturbations. So, and you can even use this clever score as a way to design as a feedback, right, to help you select a more robust model and so on. So this is one typical example how we advocate to use the clever score. So this is a hypothetical setting, and it's actually a demo that is publicly available, developed by my colleagues, right? So it's a hypothetical setting that you are a bank model developer, and you are going to choose one out of few models to deploy, right? And to ask for handwritten digital recognition when you write a check. And there are a lot of choices you can choose. There are robust models and there are non-robust models. So it's an interactive demo in the sense that the user can score, can evaluate, can decide which model they think are most robust. And you will see that the scores the users provided is actually highly correlated with the clever score we evaluated. That means this is truly a score that can tell you which the ranking of the robustness of the model. It also help the model developer and the user understand how to select a more robust model in their applications. I would like to make takeaways, right? So I hope in this lecture I convince you adversarial robustness is something we should spend more efforts on, and I'm pretty much sure that it will be a new AI standard. Right, because eventually when we are deploying our AI models, we not only want it to be accurate, we only want it to be trustworthy. And robustness is one of the milestones that the ideal model needs to achieve. Nonetheless, this robustness usually do not come for free, right? Adversarial examples can be easily created and exist in digital space as well as the physical world, and we can generate that in different domains. Even worse, usually a model with high standard accuracy does not imply the model is having good robustness. And there's always arms race in terms of adversaries using AI to gain their benefits, and how can we prevent using AI to kind of devise a better AI. So this is really an arms race. We also talk about ways that we can evaluate and improve adversarial robustness, right? Like different attack assumptions and also scenarios based on what the assumptions that you make on the attacker's capability that we call threat models. We also talk about specific defenses that leverage domain knowledge as well as more general purpose defense like adversarial training or self-propagating training or so. We also talk about how do we do scalable and efficient model training and verification to properly certify the performance of the model. Finally, I think I also make some example about how can we do adversarial machine learning beyond attacks and defenses. For example, using the lessons we learned to do model reprogramming and show it can achieve new state-of-the-art in terms of data-limited transfer learning. I often share our new research progress on my Twitter. So if you're interested, feel free to follow me, and we can have more interaction. And I'm always very happy to discuss new ideas with different researchers. Lastly, I would like to show my roadmap toward making holistic adversarial robustness, right? So ideally, a good robustness technique, right, should be model agnostic, right? Can work with different scenarios, but it also needs to leverage domain-specific knowledge. And most importantly, it needs to be practical, right? We have to make sure it would not compromise the utility of the model too much. And we have to make sure that robustness will be carried out through the life cycle of the AI model, right? Spanning from training time, testing time, and also continuous monitoring. And we talk about a lot of terms, right, that can actually be rephrased in a more general way, right? So when we are doing attack, we are not just trying to break the system. We are actually trying to find bugs in our system and find bugs before that the model is actually being deployed and being broken by others. So in a way, we are doing a lot of white hat hacker and testing before others break our own system. When we are doing defense, we are really talking about hardening our model, detecting and mitigating potential threats, right, in an active manner. And most importantly, we should develop a lot of a plug and play approach, right? Once we realize our model is broken, how can we fix our model on the spot rather than train a new model and from scratch and so on. And also verification, right? How can we certify the performance of the model in a rigorous manner to establish attack-proof certificates or make sure our models will be running safely and reliably under some constraints or some requirements. Lastly, it's about model boosting, right? How can we leverage the lessons we learn from adversarial robustness to do new data augmentation or model reprogramming or model watermarking and so on. So I think this is a very interesting space to look deeper into once we understand how can we make the model robust and so on. So there are more online resources that I recommend you can take a look, and most of them are being recorded, right, because of the pandemic. And for example, the most recent tutorial that Sayak and I gave at the CDPR are made available online, and we not only provide some technical background, we also provide some codes, hands-on codes, and well-documented GitHubs that you can try and to test these simple ideas, like, for example, how to generate adversarial examples and so on. And there are several libraries that provide a good wrapper to generate adversarial examples and do some defense, right, to the model. There are also some simple surveys that I collected that I think will be worthwhile to read to get to know more in this field. And Cho Rui and I are also writing a book on adversarial machine learning, and hopefully it will be published next year. Lastly, I also want to give some spotlight on ART. Right? This is an open source library, adversarial robustness toolbox developed and maintained by IBM. So it provides a very wide range of attack, defense, detection, and verification techniques, including a clever score or so. It also provides a nice wrapper. So it's a Python-based code base that can wrap whatever model you are using and run this adversarial robustness testing. We are also hosting an annual workshop at KDD, right? Adversarial Machine Learning Workshop called IDVML. I think it will take place next week. So if you are interested, feel free to register and check out our agenda and submit your papers there to talk to the experts in this field. And I also want to just briefly mention, right, there are multiple factors if you are thinking about making AI trustworthy. Robustness is one, but let's not forget fairness, explainability, and so on. Lastly, as for new students who want to enter this field, I have some personal some trends I observed, some personal notes I want to share. So first of all, right, we do see almost exponential growth, right, in the papers, right, associated with adversarial robustness, right. So as a researcher who have been working on this field for a while, I start to think about the sustainability of our area, right? So are we able to keep this exponential growth or not, right? If we are not thinking about new directions, or if we are not making enough scientific breakthroughs. Right? So I would like to share some trends I observed, right? I'm not saying these are bad trends, but these are something that are, I think, more will lose appeals pretty soon. And I encourage the younger students to think about something beyond these topics, right? So there are a lot of papers talking about how do I do adversarial attack on a specific task, and then how do I do black box attack on this task? How do I do hard-label black box attack on this task? And finally, how do we find adversarial examples more efficiently to a particular norm, right? So these are like great topics, but I don't think this will give us a sustainable growth, right, as time goes. Similarly, for defense, right, we do see like defense against the attack using some method, or detecting adversarial attack using some method, and then certify robustness for a specific task or specific norms, or adversarial training using more advanced technique. So again, these are like great topics, but these are really not bringing the delta we want to see in our area, right? So can we do something that is out of box, but actually, can give a larger margin than what the current methods do? And I also like a lot of reflection papers. I encourage you to read it, right? So there are a lot of papers saying all empirical defenses are vulnerable, or they are not tested properly against the adaptive white box attack. And also there are some reflection in terms of, do we really need the notion of threat model, right? Can we relax the assumption of LP norms, and what do the results give us, right? And also there's a general erosion of general robustness, right? So in addition to adversarial robustness, you can do similar research, right, through this, for example, out of sample generalization, or out of domain generalization, or domain shifts or so, right? So the similar methodology we developed for studying adversarial robustness can be easily transferred to studying the robustness of other aspects. Of course, you can also study the trade-off between adversarial robustness and other factors, right? Privacy, fairness, interpretability. I think that will make the story more complete, and also have a more holistic view of what the trade-off we have in a practical machine learning system. And finally, there are a lot of things that remain to be studied in a theoretical perspective, right? Like how easy or how hard it is to build robustness in our machine learning system, right? From both optimization perspective or computationally hardness perspective, or from the generalization perspective. So there are a lot of things that remains to be understood. Same slide. Okay, finally, I want to quickly acknowledge my colleagues and my collaborators with their support, and they'll have a nice portfolio of research assets that I summarized to you through this lecture. Now it's time for me to ask questions to me, and I will answer some on the Slack channel, on the channel. Okay, the one question is about certification. So most of the robust certification methods rely on giving specific samples as inputs. My question is, can we do robust certification in model level? Okay, yeah, so this is a great question, right? So in a sense, we are thinking, yeah, you are totally correct that these certification are like a local robustness certification. Local means it's a sample-wise class certification, right? So, and of course, we are also interested in the global certification. That means model level certification. But that is not an easy problem, because you need to first define what is the local global model certification mean to you, right? So for example, if we know the data manifold, or if we know how the training data are being generated, then it's possible we are able to kind of have overall measure on the robustness relative to the data manifold. But in general, we don't know the data distribution. All we know is a set of data samples. So I would say a global robustness, or even like class level robustness, is certification is certainly very important. And but I don't see much works on that. And for me, I think that is definitely something very important and worth pursuing as a research topic. The next question, what is my thought on invariance adversarial examples? Yes, so I think these are, again, very important question, right? So I would say in terms of invariance, right, you can probably think of there's a way to simulate these invariance transformations or through some semantic perturbations, right? Like this rotation or color change idea I described. I certainly believe a robust model, right, should have robustness to invariance changes as well. So this is also something very important. It's actually, I think there are recently more and more people talking about how can we ensure the model is robust to invariant transformation and so on. Next question. Adversarial training robust accuracy is high on MNIST compared to CFAR. Yes. Or other color images. What is the relation between adversarial attack and data? There is one. Yeah, this is a great question. So I believe, and I think there are some simple proof to show, like if your data are more complex, or the problem, the task you are solving are more complex, right? So for example, MNIST versus CFAR, right? Like, or CFAR versus ImageNet. If your model, your data are more complex, and the tasks you are solving are more difficult, like you have a 10 class classification problem all the way to 10,000 or so, then that the problem complexity and data complexity will come in and harm the accuracy and robustness for sure. So for example, people have shown that on MLSS, right, the black and white image, we can train a model that is more robust, like I think up to like up to maximum perturbation of a pixel value of 8, right? When your pixel value are ranging between 0 and 255. Sorry, no, it's more than that, right? So when you normalize that on image, on MLSS, you are able to be robust up to like 0.3 perturbation, right? When you normalize the perturbation versus the maximum range of the pixel value. However, when it goes to CFAR, right? I think the maximum certifiable range is the epsilon people usually use to rank accuracy is like 8 divided by 255, which is like a 0.03, right? So we do see we move from 0.3 to 0.03 from MLSS to CFAR. And when we move to ImageNet now, we are now struggling with the even smaller epsilon, like a 0.01 or 0.02 or so. So this problem is really challenging, and that's why I think we need to make more significant progress and maybe think outside of the box, right, and address more fundamental issues rather than making small delta to make our this area grow. So next question. So what do I think about defense methods other than adversarial training? Do I think these methods are possible to successfully defend against adaptive attack? Yeah, I would say there are possibly ways to make our model robust other than using adversarial training, right? So I would say we have made some attempts, right, like a self-progressing attack. Self-progressing robust training. So that's one way to avoid this sample-wise perturbation and to speed up the training. I'm pretty sure there could be new ways to do that. I certainly think it's very important to, one, either make the adversarial training more efficient and scalable to large training. Two, otherwise we need to think about other ways to find those robust models, right? So I think there are some recent insights showing there indeed exists robust model. It's just a matter of how do we find the robust model. Maybe gradient descent or like min-max optimization is not sufficient to find those good sweet spots, and that basically motivates us what is the right way to find those good models. Next question, when I talk about the trends, what are the new research instead of the attack and defense? Yeah, so I don't know for completely no, right? So what I was just saying is if we focus too much on publishing papers with those topics I just, similar titles, right, I just listed, I don't think we are going anywhere too far in the future. On the other hand, if researchers in our community are willing to take risks and be more aggressive, right, and do things in a different way, or try to avoid publishing papers like that, I think we can make more sustainable and also a significant growth in the research area. So for me, I personally, like recently I've been focusing on different ideas like reprogramming or thinking about trying to see what are the other ways that we didn't think of to improve robustness. But this is certainly not an easy problem to address, in my opinion. I think I basically answered every question. Yeah, okay, I think that will be the end of my talk. Sounds like back to you.
Yeah, thank you very much for the great talk. And so finally, I have one general question for you. So in many applications, how much should we care about like this kind of adversarial attacks? So because a lot of times there's often a trade-off between, say, robustness and standard test accuracy and even computational complexity. And so when you say you want to provide a machine learning service and you care about adversarial robustness, but so you do a lot of effort, but most people wouldn't appreciate that, and even they say, oh, the performance on standard or normal data drops. Yeah, how do you?
Yeah. So I have several thoughts on that, right? So first of all, although most of our papers are motivated by this adversarial example in the image domain, the more I work on it, the less I think it will be really matters, right? So I think for images, it's very difficult to make our system as robust to a human level, and also we observe very obvious trade-off between accuracy and robustness in the image domain. However, if we go to other domains like natural language processing, what I discovered is there may not be a trade-off. Like you can simply generate this adversarial text, and then you augment those texts and retrain a model. Usually, that model can be more robust and also more accurate at the same time. So, in a way, adversarial examples, if you define it properly, it's actually a very powerful data augmentation tool that can improve not only the robustness but also the performance of your model. But again, we need to spend more efforts, right? Not looking into images, but looking into other domains to make concrete cases that the robustness matters. Especially, I would encourage researchers to look into this safety critical application, maybe in the industrial domain, like control systems or like some sensor or some machine learning model with sensors, right? For example, maybe for industrial application like aircraft autonomous driving cars, maybe too complicated, but maybe like autonomous drones or aircrafts that some small pieces that are actually require high reliability and robustness, and even some safety constraints like what we recently saw in this safe reinforcement learning research, right? So I think those domains are probably easier to make improvement because these domains usually have a much lower dimension than the image space. And then they also have a very desperate need to make their systems robust, or at least satisfy some properties like a safe RL, for example. So I think we have to look into the right domains to make the breakthrough and not to focus too much on images.
Okay, yeah, thank you very much for the great talk, and thanks everyone for attending this lecture. And don't forget that we'll have a panel discussion session on trustworthy machine learning on August 18th. And so we'll see Dr. Ping Chen very soon. Yeah. Okay. See you.
Thank you.
Thank you. Bye-bye.